Chapter 1. The structure that should not exist. There are discoveries in science that feel inevitable. They fit neatly into existing frameworks. They confirm what theory already predicted. They strengthen confidence in the rules we believe govern reality. And then there are discoveries that feel wrong. Not because they are uncertain, or poorly measured, or controversial due to lack of data, but because they exist in direct tension with what should be possible. This is one of those discoveries. Somewhere deep in the observable universe lies a structure so vast that its very existence strains the logic of modern cosmology. Not metaphorically, not philosophically, mathematically. According to the equations that describe how matter clumps, how gravity competes with cosmic expansion, and how structure grows over billions of years, this thing should not be there. And yet, it is. It stretches across roughly 1.4 billion light-years of space, a scale so large that describing it as big fails to capture the problem. The issue is not that it is impressive. The issue is that it violates expectations built into the foundations of how we understand the universe. Expectations that are not arbitrary. Expectations derived from observation, simulation, and physical law. This structure is known as the Hercules Corona Borealis Great Wall, and its discovery represents more than a curiosity. It represents a challenge, one that forces cosmologists to confront an uncomfortable possibility, that the rules we rely on to describe the universe at its largest scales may be incomplete. To understand why this matters, we need to be clear about what is being claimed. The universe is vast. No one disputes that. It contains trillions of galaxies, each separated by enormous distances. But vastness alone is not the problem. The universe is allowed to be large. What it is not allowed to be, according to one of the central principles of cosmology, is uneven in a particular way, beyond a particular scale. Modern cosmology rests on a deceptively simple idea that if you zoom out far enough, the universe smooths out. Galaxies cluster. Clusters form superclusters. Filaments stretch across space. Voids open up between them. But eventually, when you average over sufficiently large volumes, the universe should look statistically the same everywhere. No special directions, no preferred locations, no gigantic coherent features dominating the cosmic landscape. This assumption is not philosophical optimism. It is supported by evidence. It underpins the equations that describe cosmic expansion. It allows us to model the evolution of structure from the earliest moments after the Big Bang to the present day. Without it, much of modern cosmology collapses. And yet, here is a structure that appears to ignore that rule. The Hercules Corona Borealis Great Wall is not merely a concentration of galaxies. It is a connected region of enhanced density, extending so far across space that it challenges the scale at which uniformity is supposed to emerge. If confirmed as a real coherent feature, and evidence increasingly suggests that it is, it exists well beyond the theoretical upper limit for structures formed by gravitational clustering. This is where the discomfort begins, because the models that predict how galaxies form and cluster are not speculative. They are tested. Simulations that begin with the tiny density fluctuations observed in the early universe produce a cosmic web strikingly similar to what we observe today. Filaments, clusters, voids, all emerge naturally. But these simulations also impose limits. They tell us how quickly matter can collapse. They tell us how far gravity can organize matter across expanding space. They tell us that beyond a certain scale, structure should dissolve into statistical uniformity. The Great Wall exceeds that scale by a wide margin. What makes this particularly troubling is not just the wall's size, but its age. We are not observing this structure as it exists today. We are seeing it as it was billions of years ago. The light reaching us left this region when the universe was still relatively young, less than a third of its current age. At that time, structure formation should have been even more limited, not more advanced. Gravity works slowly. On cosmic scales, it requires enormous time to draw matter together across vast distances. The universe was expanding faster in its youth, making this process harder, not easier. And yet, the Great Wall appears to have already existed in recognizable form during that early epoch. This creates a timing problem as severe as the size problem. If this structure is real, and increasingly the data suggests that it is, then either something unusual happened in the early universe, or our understanding of how structure forms is missing a crucial piece. Neither option is comfortable. Both demand careful examination. Naturally, the first response from scientists was skepticism. Extraordinary claims require extraordinary evidence. Large-scale patterns can emerge by chance. Human beings are exceptionally good at finding structure where none exists. Random distributions, when sampled unevenly, can produce apparent clusters. The universe is large. Statistical flukes are inevitable, but this explanation begins to weaken under scrutiny. The methods used to detect the Great Wall are independent of traditional galaxy surveys. Instead of relying solely on visible galaxies, researchers examined the spatial distribution of gamma-ray bursts, brief, intensely energetic flashes that mark the deaths of massive stars or the mergers of compact objects. These events can be detected across vast cosmic distances, far beyond the reach of most galaxy catalogues. Gamma-ray bursts do not occur randomly. They trace star-forming regions, and star formation traces galaxies. When an unexpected concentration of these bursts appeared in a specific region of the sky, it raised a red flag. When that concentration persisted across multiple analyses, using different datasets and methods, skepticism gave way to concern. This was not noise. What emerged was a picture of a vast, sheet-like arrangement of matter, spanning a region so large that it should have been smoothed away by the statistical uniformity of the universe. A wall, not in the sense of a solid barrier, but in the sense of a coherent overdensity extending across an enormous volume of space. The implications of this are subtle, but profound. If the Great Wall is a genuine feature of the cosmic web, then either the universe is less uniform on large scales than we thought, or the processes that govern structure formation allow for rare but extreme exceptions. In either case, the assumptions that simplify our models become less secure. This does not mean cosmology is broken. It does mean it is being tested at its limits. Science advances not by ignoring anomalies, but by interrogating them. Sometimes anomalies disappear under better data. Sometimes they reveal errors in measurement or interpretation. And sometimes, rarely, they point toward deeper truths that require us to refine our understanding of reality. The Hercules corona, Borealis Great Wall, sits uncomfortably in this third category. It is too large to be easily dismissed, too coherent to be ignored, too consistent across analyses to be written off as coincidence, and too challenging to be accommodated without careful reconsideration of long-held assumptions. This is not a story about tearing down physics. It is a story about confronting the edge of what physics currently explains, about standing at the boundary between prediction and observation, where theory hesitates and data refuses to cooperate. In the chapters that follow, we will build the necessary foundation to understand why this structure is such a problem. We will examine how the universe organizes itself, what limits that organization, and why those limits exist. We will explore how the Great Wall was discovered, how its size was measured, and why its existence forces cosmologists to ask questions they would rather not have to ask. For now, it is enough to understand this. The universe contains a structure that appears to violate its own rules, not dramatically, not explosively, but quietly, persistently, and uncomfortably. And those are often the most important discoveries of all. Chapter 2. Understanding Cosmic Scale Before the Problem Appears. Before the Hercules corona Borealis Great Wall can be understood as a problem, it must first be understood as a scale, not just a large object, but a violation of hierarchy, because the universe is not a random scattering of matter. It is organized in layers. Each layer has a characteristic size, and for decades, astronomers believed they understood where those layers end. To appreciate why the Great Wall is troubling, we need to climb that hierarchy step by step, starting from the familiar and moving outward until intuition begins to fail. The smallest meaningful unit of cosmic structure is the planetary system. Earth, for example, has a diameter of about 12,700 kilometers. From a human perspective, this is vast. Entire civilizations rise and fall without ever traversing its full surface. But cosmically, Earth is negligible. It is a speck bound to a star by gravity, one of countless such systems scattered through the galaxy. The solar system extends far beyond Earth, reaching roughly 4.5 billion kilometers from the Sun to the orbit of Neptune. Even this scale defies practical travel. The fastest spacecraft humanity has ever launched would require tens of thousands of years to cross it. Yet in cosmic terms, the solar system is still microscopic. Stars themselves are separated by far greater distances. The nearest star to the Sun, Proxima Centauri, lies over 4 light-years away. A light-year is nearly 10 trillion kilometers. At that scale, even interstellar space becomes an ocean of emptiness. Stars are islands of matter separated by vast voids. Galaxies emerge as the next level of structure. The Milky Way contains hundreds of billions of stars and spans roughly 100,000 light-years from edge to edge. It is massive beyond comprehension, yet galaxies are not isolated. Gravity pulls them together into groups. Our galaxy belongs to the local group, a gravitationally bound collection of dozens of galaxies spanning about 10 million light-years. Within this region, galaxies orbit one another, slowly drifting and occasionally merging. Over cosmic time, these interactions reshape galaxies entirely. Beyond galaxy groups lie clusters and superclusters. The Virgo supercluster, for example, contains thousands of galaxies across a region more than 100 million light-years wide. These structures represent the largest gravitationally influenced systems that were once thought to exist. And for a long time, astronomers believed this was essentially the end of the hierarchy. Not because nothing larger could exist in principle, but because the universe itself imposes limits. Those limits come from two competing forces: gravity and expansion. Gravity pulls matter together. Expansion pushes everything apart. Structure formation is a race between these two effects. In the early universe, matter was distributed almost uniformly. Tiny variations in density, no more than 1 part in 100,000, were present. These fluctuations are preserved in the cosmic microwave background radiation, the afterglow of the Big Bang. Over billions of years, gravity amplified those small differences. Slightly denser regions attracted more matter. Over time, these became galaxies, clusters, and filaments. But gravity does not act instantly. It works gradually, limited by distance, mass, and the age of the universe itself. Meanwhile, cosmic expansion stretches space, increasing the distances gravity must overcome. This imposes a natural ceiling on how large coherent structures can grow. This is where the concept of the cosmic web enters the picture. When astronomers began mapping galaxy positions in 3 dimensions, they discovered that galaxies are not scattered randomly. Instead, they trace a vast, interconnected network of filaments, sheets, and nodes. Dense filaments of galaxies stretch across hundreds of millions of light-years, connecting massive clusters. Between these filaments lie enormous voids, regions almost empty of matter. The universe at its largest scales resembles a sponge or foam. Matter outlines the boundaries of empty bubbles. This structure arises naturally from gravitational evolution, acting on initial density fluctuations. It is not imposed by design, it is emergent. Crucially, however, this web has a characteristic scale. When you average galaxy density over regions larger than a few hundred million light-years, the universe appears statistically uniform. The filaments and voids blur together. Overdensities and underdensities cancel out. No region appears fundamentally special. This behavior is formalized in what cosmologists call the cosmological principle, the assumption that the universe is homogeneous and isotropic on sufficiently large scales. Homogeneous means roughly the same everywhere. Isotropic means the same in all directions. This principle is not philosophical convenience. It is observationally supported. Measurements of the cosmic microwave background show extraordinary uniformity across the entire sky. Galaxy surveys confirm that beyond scales of roughly 300–400 million light-years, matter distribution smooths out. From this principle emerges a crucial prediction. There should be a maximum size beyond which coherent structures cannot exist. That limit is not sharply defined, but it is estimated to be around 300–400 million light-years. Structures larger than this should not behave as single connected entities. Any apparent clustering beyond this scale should be statistical coincidence, not physical reality. This expectation has guided cosmology for decades, so when astronomers discovered filaments approaching 500 million light-years in length, eyebrows were raised, but the models survived. These structures sat near the upper boundary of what was allowed. Rare, but plausible. Then came discoveries that pushed further. Walls spanning nearly 1 billion light-years, rings of matter stretching across cosmic volumes. And finally, the Hercules Corona Borealis Great Wall, stretching 1.4 billion light-years, far beyond the predicted ceiling. At this point, the issue is no longer one of interpretation. It is one of scale violation. The Great Wall is not simply another filament or cluster. It exists on a scale where homogeneity should dominate, where structure should dissolve into average density, where the universe should stop having features, but it does not. Understanding why this is troubling requires holding two truths at once. First, the universe is vast and structured. Second, that structure has limits. The Great Wall sits beyond those limits. That does not automatically mean the cosmological principle is false, but it does mean it is being tested in the most demanding way possible, not by small discrepancies, but by the discovery of something that exists precisely where it should not. Before we can decide what this means, we must understand how the Great Wall was detected in the first place, and why its discovery could not be dismissed as a quirk of galaxy surveys. That story begins not with galaxies, but with explosions powerful enough to be seen across the entire observable universe. And that is where we turn next. Chapter 3. How gamma-ray bursts revealed an impossible structure. The Hercules Corona Borealis. Great Wall was not discovered by looking for galaxies. That detail matters. Most of what we know about large-scale cosmic structure comes from galaxy surveys, long, methodical projects that catalog the positions and distances of millions of galaxies. These surveys are powerful, but they have limits. They are biased toward brighter galaxies. They struggle at extreme distances, and they require enormous observational effort to map three-dimensional space accurately. The Great Wall entered astronomy from a completely different direction. It was revealed through gamma-ray bursts, the most energetic explosions known in the universe. Gamma-ray bursts, or GRBs, are brief but extraordinarily intense flashes of high-energy radiation. They can last anywhere from a fraction of a second to several minutes, and during that short time, they can release more energy than the Sun will emit over its entire lifetime. For a few seconds, a single GRB can outshine every galaxy in the observable universe combined. These events are thought to originate from two main processes. Long-duration gamma-ray bursts occur when extremely massive stars collapse into black holes, producing relativistic jets that pierce through the dying star and beam energy outward. Short-duration bursts are associated with the merger of neutron stars, dense stellar remnants spiraling together until they collide in a catastrophic release of energy. What makes gamma-ray bursts so valuable for cosmology is not just their power, but their reach. They can be detected across billions of light-years. A GRB does not need to occur in a bright galaxy. It does not need to sit in a cluster. It does not even need a massive host. As long as a massive star forms, or neutron stars merge, the burst can be seen. This makes GRBs a unique tracer of matter distribution at extreme distances, especially in regions where traditional galaxy surveys are incomplete. In the early 2010s, astronomers were compiling a growing database of GRBs detected by space-based observatories. Each burst came with a sky position, and in many cases, a measured redshift, allowing its distance to be determined. Over time, this created a three-dimensional map, not of galaxies themselves, but of where these catastrophic events were occurring in the universe. Initially, the assumption was simple. GRBs should be roughly randomly distributed when averaged over large enough scales. Since they trace star formation and stellar death, their distribution should mirror the overall distribution of galaxies. That assumption held, until it didn't. When researchers plotted the locations of GRBs in three-dimensional space, they noticed something unusual. In a specific region of the sky, in the direction of the constellations Hercules and Corona Borealis, there was a statistically significant excess of gamma-ray bursts. At first glance, this could have been dismissed as coincidence. After all, random data produces patterns. Given enough points, clusters will appear. The human brain is exceptionally good at finding structure, even where none exists. Astronomers are acutely aware of this risk, especially when dealing with sparse datasets. So the initial finding was treated cautiously. The first step was to ask a simple question: is this clustering real, or is it an artifact of observational bias? Gamma-ray detectors do not observe the sky uniformly. Some regions are monitored more often. Some directions are blocked by Earth at certain times. Instrument sensitivity varies. Any of these effects could produce an apparent clustering that has nothing to do with cosmic structure. To test this, researchers carefully modeled the detection sensitivity of the instruments involved. They accounted for sky exposure, detector downtime, and selection effects. They asked whether the observed clustering exceeded what would be expected, given how and where the telescopes were actually looking. It did. The excess remained even after correcting for observational bias. The next question was whether the clustering existed in distance, not just direction. A projection of unrelated objects at different distances can appear clustered on the sky, even if they are not physically connected. To rule this out, astronomers examined the redshifts of the GRBs in the region. What they found was striking. The bursts were not scattered across cosmic time. They were concentrated within a relatively narrow redshift range. That meant they were occurring at similar distances. In 3 dimensions, the GRBs traced a coherent structure. This was the moment the discovery crossed from curiosity into anomaly. Gamma-ray bursts are markers of galaxies. If many GRBs occur in the same region of space, it implies many galaxies exist there as well. Not just a slight overdensity, but a massive concentration of matter. Further statistical analysis confirmed that the probability of such a clustering occurring by chance was extremely low. Independent teams applied different methods and reached similar conclusions. The signal persisted. The structure was real. Only then did astronomers begin to interpret what the GRB distribution was actually tracing. What emerged was not a point-like cluster or a filament, but something far larger, a sheet-like structure extending across an enormous volume of space, a wall of galaxies stretching roughly 1.4 billion light-years in its longest dimension. This alone would have been remarkable. But the real shock came when researchers calculated how old the universe was when the light from this structure was emitted. The Great Wall lies roughly 10 billion light-years away. That means we are seeing it as it existed when the universe was only about 3.8 billion years old, less than 1/3 of its current age. At that epoch, cosmic structure was still forming. Galaxies were smaller, more chaotic, and actively assembling. Filaments and clusters were emerging, but the cosmic web was not yet fully developed. And yet, this structure already existed, not in embryonic form, not as a loose suggestion of clustering, but as a coherent, enormous wall spanning over 1 billion light-years. This is where the discovery became deeply problematic. According to standard models of structure formation, there simply had not been enough time for gravity to organize matter over such vast distances. Even with dark matter accelerating collapse, even with favorable initial conditions, the math does not allow structures of this scale to form so early. The GRB data did not merely suggest a large structure, it placed that structure in a time period where it should have been impossible. That is why the discovery could not be brushed aside. It was independent of traditional galaxy surveys. It relied on a completely different tracer of matter. It survived multiple layers of statistical scrutiny, and it pointed to a structure that violated theoretical expectations in both size and timing. The Great Wall was not something astronomers were searching for. It was something they stumbled into while looking for something else. And that makes it far more dangerous to existing theories, because when an anomaly appears unexpectedly through an independent method and refuses to disappear under analysis, it forces a deeper question, not about data quality, but about understanding. To see why this structure is such a profound challenge, we now have to confront the principle it seems to violate. The idea that, beyond a certain scale, the universe should have no walls at all. Chapter 4. The Cosmological Principle and the Maximum Size of Structure. To understand why the Hercules Corona Borealis Great Wall is so unsettling, we need to step away from observation and into the philosophical and mathematical foundation of modern cosmology. This foundation rests on a single, deceptively simple idea: the cosmological principle. The cosmological principle is not a law of physics. It is an assumption, but one that underpins nearly everything we believe about the universe on the largest scales. At its core, the principle states two things. First, the universe is homogeneous on sufficiently large scales. That means that if you zoom out far enough, matter is distributed roughly evenly. No region of the universe is fundamentally special or privileged. Second, the universe is isotropic. It looks roughly the same in every direction. There are no preferred axes, no cosmic up or down, no center toward which everything is arranged. This does not mean the universe is smooth everywhere. Clearly, it is not. Galaxies exist, clusters exist, voids exist. The cosmological principle allows for all of this. What it says is that these variations average out when considered across sufficiently large volumes of space. In other words, structure is allowed, but only up to a point. The universe can be clumpy on small and intermediate scales, but beyond a certain threshold, those clumps must blur into statistical uniformity. That threshold is not arbitrary. It emerges from both observation and theory. Observationally, astronomers have tested homogeneity by counting galaxies within increasingly large volumes of space. On small scales, the density varies wildly. Some regions are crowded with galaxies, others are nearly empty. But as the volume increases, these fluctuations diminish. Beyond scales of roughly 300 to 400 million light-years, galaxy density becomes remarkably uniform. This empirical result strongly supports the cosmological principle. Theoretically, the principle is reinforced by our understanding of cosmic history. The early universe, as revealed by the cosmic microwave background, was extraordinarily uniform. Temperature variations across the entire sky are on the order of 1 part in 100,000. These tiny fluctuations are the seeds of all structure we see today. Gravity amplifies these fluctuations over time. Regions that were slightly denser attract more matter, becoming denser still. Regions that were slightly underdense lose matter, becoming voids. This process produces the cosmic web: filaments, nodes, sheets, and voids. But gravity operates at a finite speed and over a finite time. The universe is 13.8 billion years old. That fact alone places a hard limit on how much structure can form. Matter separated by vast distances simply has not had enough time to interact gravitationally in a coordinated way. Moreover, the expansion of the universe works against structure formation. As space expands, it pulls matter apart. Gravity must fight this expansion to bring matter together. On very large scales, expansion wins. When these factors are combined, initial fluctuation size, gravitational growth rate, cosmic expansion, and finite age, they produce a clear prediction. There is a maximum size beyond which coherent structures cannot exist. This theoretical upper limit is generally placed at around 370 million light-years. Structures larger than this should not be gravitationally connected. They should not behave as unified entities. Any apparent structure beyond this scale should be the result of chance alignments or statistical fluctuations, not physical organization. This limit is not merely a guideline. It emerges from simulations that begin with conditions measured directly from the early universe and evolve them forward using known physics. These simulations reproduce the observed cosmic web remarkably well, up to that scale. They do not naturally produce structures exceeding it by factors of 3 or 4. This is where the Great Wall becomes deeply problematic. At 1.4 billion light-years, it exceeds the expected maximum scale by nearly an order of magnitude. Even if one adopts conservative definitions of its boundaries, it remains vastly larger than what the cosmological principle comfortably allows. The problem is not just size, it is coherence. If the universe were homogeneous beyond a few hundred million light-years, then averaging over a region the size of the Great Wall should smooth out any density contrast. The wall should dissolve into the background when viewed at that scale. But it doesn't. It remains a detectable overdensity. It maintains spatial continuity. It appears as a sheet-like structure rather than a random scatter. This suggests one of 3 uncomfortable possibilities. The first is that the cosmological principle is wrong, or at least incomplete. Perhaps the universe is not as homogeneous as we think on the largest scales. Perhaps there are preferred regions, or unusually large fluctuations, that survive averaging. The second is that our models of structure formation are missing something fundamental. Perhaps gravity behaves differently on extreme scales. Perhaps dark matter has properties that allow faster or more coordinated collapse. Perhaps initial density fluctuations were not as uniform as inflation predicts. The third possibility is that the structure is not truly coherent in a physical sense, that what we are seeing is a statistical artifact amplified by how we define and detect structure. Each of these possibilities carries serious implications. Abandoning or weakening the cosmological principle would require rethinking the foundations of cosmology. Our equations describing expansion, curvature, and energy content all rely on large-scale homogeneity. Removing it would destabilize much of modern theory. Altering structure formation physics would require new components or interactions, especially involving dark matter or dark energy, entities we already struggle to understand. Dismissing the structure as statistical would require explaining why multiple independent analyses, using different tracers, converge on the same conclusion. At present, none of these options is fully satisfying. Most cosmologists adopt a cautious middle ground. The cosmological principle is treated as an approximation, not an absolute rule. Rare exceptions may exist, outliers produced by extreme but statistically permissible fluctuations in the early universe. In this view, the Great Wall is not a refutation of cosmology, but a stress test. It represents the universe pushing the limits of what is allowed without breaking the rules entirely. But even this interpretation raises a troubling question. If such a massive structure exists at all, especially so early in cosmic history, then how close are we to the true boundary? Are there larger structures waiting to be discovered? Or does the universe consistently produce objects right at the edge of theoretical tolerance? To answer that, we must examine whether the Great Wall is truly unique, or part of a broader pattern of extreme structures that collectively hint at something deeper. That investigation leads us to compare it with other enormous cosmic features, and to ask whether the universe has been quietly challenging our assumptions all along. Chapter 5. Discovery through gamma-ray bursts, seeing the invisible. The Hercules Corona Borealis Great Wall was not discovered the way most cosmic structures are. Astronomers did not first see it as a faint smear of galaxies in deep optical surveys, nor did it reveal itself through the slow accumulation of redshift measurements across decades. Instead, it announced its presence indirectly, through some of the most violent and luminous events in the universe: gamma-ray bursts. This alone sets the Great Wall apart. It was not found by mapping galaxies themselves, but by tracing cosmic explosions that briefly outshine entire galaxies and can be seen across nearly the full observable universe. Gamma-ray bursts, or GRBs, are intense flashes of high-energy radiation, lasting anywhere from milliseconds to several minutes. They occur when massive stars collapse into black holes, or when compact objects like neutron stars merge. In either case, enormous amounts of energy are released in tightly collimated jets moving at nearly the speed of light. When one of these jets happens to be pointed toward Earth, we detect a gamma-ray burst. What makes GRBs special is their visibility. A single burst can be detected from billions of light-years away. They are among the brightest events known, briefly dominating the gamma-ray sky. Because of this, they serve as cosmic beacons, markers of star-forming galaxies at extreme distances. Astronomers began cataloguing GRBs in large numbers in the late 20th and early 21st centuries using space-based observatories such as Swift and Fermi. Over time, these missions built extensive datasets recording the positions, durations, and redshifts of hundreds of bursts. Initially, these catalogues were used to study the physics of the bursts themselves. But eventually, researchers began asking a different question. Are GRBs randomly distributed in space, or do they trace large-scale structure? If GRBs occur in galaxies, and galaxies cluster into filaments and walls, then GRBs should statistically trace those same structures, especially regions of active star formation. In 2013, a team of astronomers decided to test this idea by plotting the three-dimensional positions of long-duration gamma-ray bursts. These bursts are associated with massive star collapse and therefore occur preferentially in star-forming galaxies. By measuring their redshifts, the researchers reconstructed where in cosmic history and space these explosions originated. What they found was unexpected. When the bursts were mapped in 3 dimensions, a significant overdensity appeared in one region of the sky, roughly in the direction of the constellations Hercules and Corona Borealis. This was not a subtle effect. There were far more GRBs in this region than would be expected if bursts were randomly distributed. At first, skepticism was warranted. GRB datasets are inherently sparse compared to galaxy surveys. Hundreds of data points spread across billions of light-years leave room for chance alignments and selection effects. The team, therefore, subjected the signal to rigorous statistical testing. They examined whether the overdensity could be explained by observational bias. Were telescopes more sensitive in that direction? Had certain regions of the sky been observed longer than others? Could instrumental effects or detection thresholds be responsible? These possibilities were systematically ruled out. The overdensity persisted across different datasets, detection methods, and statistical approaches. The probability that the clustering was due to random chance was found to be extremely low. The implication was profound. If gamma-ray bursts trace galaxies, then this region must contain a massive concentration of galaxies, a structure far larger than anything predicted by standard cosmology. Follow-up analyses reinforced this conclusion. The spatial extent of the GRB overdensity corresponded to a structure approximately 1.4 billion light-years long. This was not a point cluster or a small filament. It was a vast sheet or wall extending across an enormous volume of space. Crucially, the redshifts of the bursts indicated that this structure existed when the universe was only about 3.8 billion years old. This timing intensified the problem. Not only was the structure enormous, it was already in place at an early epoch when structure formation should have been far less advanced. The use of GRBs as tracers also helped address a key criticism often raised against large-scale structures: projection effects. When galaxies are mapped in 2 dimensions, unrelated objects at different distances can appear aligned along our line of sight, creating the illusion of structure. Gamma-ray bursts mitigate this problem because their redshifts are measured individually. Each burst has a known distance. The clustering observed in the Great Wall region is therefore genuinely 3-dimensional, not a projection artifact. This makes the detection especially robust. Still, astronomers were cautious. They did not immediately declare the Great Wall a definitive violation of cosmological principles. Instead, they framed it as a statistical anomaly, a structure that appears real but sits uncomfortably with existing theory. Independent teams reanalyzed the data using different statistical techniques. Some focused on nearest neighbor analyses, others on correlation functions. The results consistently pointed to the same conclusion: the overdensity was real and significant. What made the discovery even more intriguing was that GRBs trace only certain types of galaxies, those with active star formation and massive stars. This means the detected structure is likely just the visible tip of a much larger underlying mass distribution dominated by dark matter. In other words, the Great Wall is not merely a concentration of luminous galaxies. It is almost certainly a massive dark matter structure, with normal matter tracing its densest regions. This raises a deeper issue. Dark matter is thought to form the scaffolding of cosmic structure. It collapses first, forming filaments and sheets into which gas falls, eventually forming stars and galaxies. If galaxies are arranged into a 1.4 billion light-year wall, then dark matter must have formed an even larger coherent structure beneath them. That brings us back to the theoretical limits imposed by the cosmological principle and structure formation models. According to those models, dark matter itself should not organize into structures of this scale within the available cosmic time, and yet here it appears to have done exactly that. The discovery through gamma-ray bursts therefore did more than reveal a new structure. It exposed a potential gap between observation and theory, one that could not be easily dismissed as an artifact of galaxy surveys or selection bias. It also demonstrated the power of unconventional observational methods. The Great Wall might have remained hidden for much longer if astronomers had relied solely on traditional galaxy mapping. GRBs acted as cosmic flares, briefly illuminating a structure that would otherwise blend into the distant background. This discovery marked a turning point. The question was no longer whether the Great Wall existed, but what its existence meant. To answer that, astronomers needed to compare it with other large structures and ask whether it was truly unique or part of a troubling pattern. That comparison is where the tension with cosmology deepens even further. Chapter 6: The Cosmological Principle, where the wall breaks expectations. To understand why the Hercules Corona Borealis Great Wall is such a serious problem for cosmology, we need to examine the foundational assumption it appears to violate. This assumption is not a minor detail or a convenient simplification. It is one of the pillars upon which modern cosmology is built. It is known as the cosmological principle. The cosmological principle states that, on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means that the universe has roughly the same average properties everywhere. Isotropic means that it looks roughly the same in every direction. Together, these ideas imply that no region of the universe is fundamentally special when viewed on large enough scales. This principle does not deny the existence of galaxies, clusters, or voids. On small and intermediate scales, the universe is obviously structured. Matter clumps, galaxies form, filaments stretch between dense regions, and enormous voids open up between them. The cosmological principle applies only after you average over a sufficiently large volume of space. Once you do, the irregularities are supposed to smooth out. This idea is not philosophical guesswork. It is strongly supported by observation. The most compelling evidence comes from the cosmic microwave background, the faint afterglow of the Big Bang. When astronomers map this radiation across the sky, they find it is astonishingly uniform. After correcting for our motion through space, temperature differences from one direction to another are only about 1 part in 100,000. This tells us that the early universe was extraordinarily smooth. Large-scale galaxy surveys reinforce this picture. When astronomers count galaxies within increasingly large volumes, they find that beyond a certain scale, roughly a few hundred million light-years, the average density converges to a constant value. Clumps and voids still exist, but statistically, the universe evens out. From this emerges a crucial implication. There is a maximum scale beyond which coherent structures should not exist. Calculations based on gravity, cosmic expansion, and the age of the universe suggest that structures larger than about 300 to 400 million light-years should be rare and transient. Beyond this scale, the universe should behave like a smooth fluid rather than a structured network. This limit is not arbitrary. It arises from the finite amount of time gravity has had to act since the Big Bang. Structure formation is a slow process. Matter begins nearly uniformly distributed. Tiny density fluctuations grow under gravity, gradually pulling matter together. But gravity must compete with the expansion of space itself, which works to pull matter apart. There is simply not enough time for gravity to organize matter into coherent structures spanning billions of light-years, especially in the early universe. This is where the Hercules Corona Borealis Great Wall becomes deeply problematic. At one point, 4 billion light-years in length, it exceeds the expected homogeneity scale by nearly an order of magnitude. Even more troubling, it existed when the universe was less than 4 billion years old. At that epoch, structure formation should have been even more limited than it is today. In other words, the Great Wall is not just large. It is too large, too early. If the cosmological principle holds strictly, then such a structure should not be physically meaningful. It should be a statistical illusion, an apparent alignment produced by chance fluctuations or observational bias. But as we saw in the previous chapter, multiple analyses strongly suggest the structure is real. This creates a tension that cosmology cannot easily resolve. One option is to weaken the cosmological principle. Perhaps homogeneity only emerges on larger scales than previously thought. Perhaps the universe is statistically uniform only when averaged over volumes much larger than we assumed, but this creates problems of its own. If the homogeneity scale is larger, then many existing simulations of cosmic structure need to be re-evaluated. Predictions about galaxy clustering, dark matter distribution, and the growth of structure would all shift. Another possibility is that the Great Wall is a rare statistical outlier. In a universe as vast as ours, even extremely improbable configurations can occur somewhere. If the probability of forming a structure this large is tiny but non-zero, then finding one may not violate the cosmological principle outright. This analogy is often compared to rolling dice. If you roll enough dice often enough, you will eventually see an unlikely result. The universe contains trillions of galaxies and an enormous number of independent regions. Rare events may be expected to occur occasionally. However, this explanation depends critically on how rare the Great Wall actually is. If its probability is low but reasonable, then its existence is tolerable. If its probability is astronomically small, then its existence becomes a genuine crisis. Current estimates place it uncomfortably in between. The structure is rare enough to be surprising, but not so rare that it is impossible. This ambiguity keeps the debate open. There is also the issue of definition. The Great Wall is not a solid object with sharp boundaries. It is a region of enhanced density. Deciding where it begins and ends requires choosing a threshold. Different thresholds yield different sizes. Some critics argue that conservative definitions reduce its size enough to ease the tension. But even with cautious definitions, the structure remains extraordinarily large. The deeper concern is not just size, but coherence. The Great Wall appears to be a connected structure, not a loose aggregation of unrelated filaments. That coherence is precisely what the cosmological principle predicts should disappear at such scales. If the universe truly smooths out beyond a few 100 million light-years, then walls spanning over 1 billion light-years should blur into the background. They should not stand out as distinct entities. And yet, this one does. This does not mean the cosmological principle is wrong, but it does mean it may be approximate rather than absolute. It may describe the universe well on average, while allowing for rare deviations produced by unusual initial conditions. Such deviations would trace back to the earliest moments after the Big Bang, when quantum fluctuations were stretched to cosmic scales. Most fluctuations were small, but some may have been slightly larger, seeding regions where structure grew faster and larger than average. If the Great Wall originated from such an unusually large fluctuation, then it becomes a relic of primordial randomness, rather than a failure of physics. Still, this explanation remains speculative. What is clear is that the Great Wall sits at the edge of what cosmology can comfortably explain. It forces theorists to re-examine assumptions about homogeneity, growth rates, and the role of dark matter in shaping the universe. The cosmological principle survives, but it does so under pressure. In the next chapter, that pressure intensifies as we compare the Great Wall to other massive structures and ask whether it is truly unique or part of a growing pattern that cosmology can no longer ignore. Chapter 7. Other giant structures and why this one is different. Once the Hercules Corona Borealis Great Wall entered the discussion, a natural response followed. Is it really unique? Cosmology has faced surprises before. Other enormous structures have been discovered, and each time, theory adjusted without collapsing. To understand whether this wall truly breaks physics, it must be placed in context alongside other large-scale cosmic structures, and that comparison reveals why this case is fundamentally different. The first precedent often cited is the CFA-2 Great Wall, discovered in 1989. At the time, it shocked astronomers. Spanning roughly 500 million light-years, it was far larger than anything previously known. The discovery forced cosmologists to confront the fact that galaxies were not distributed randomly, but organized into immense sheets and filaments. However, after careful analysis, the CFA-2 Great Wall was found to sit near, but not decisively beyond, the theoretical limits imposed by the cosmological principle. Its thickness, geometry, and internal structure placed it at the extreme edge of what models could allow, but still within them. More than a decade later came the Sloan Great Wall, identified in data from the Sloan Digital Sky Survey. This structure extended close to 1.4 billion light-years, seemingly rivaling the Hercules Corona Borealis Great Wall in size. At first glance, this appeared to weaken the argument that the newer wall was exceptional, but the resemblance is misleading. The Sloan Great Wall is not a single coherent structure in the same sense. It is composed of multiple connected filaments and superclusters identified through galaxy redshift surveys. Its extent depends heavily on how connections are defined and where boundaries are drawn. When conservative definitions are applied, its effective scale drops significantly. While still enormous, it behaves more like an extended network than a single continuous wall. The Hercules Corona Borealis Great Wall differs in two crucial ways. First, how it was detected. It was not discovered through traditional galaxy surveys, which can suffer from selection effects, incomplete coverage, and projection ambiguities. Instead, it was identified through the spatial distribution of gamma-ray bursts, among the brightest and most distant signals in the universe. Gamma-ray bursts act as beacons marking sites of massive star death across vast cosmic distances. An overdensity of these events strongly implies an underlying overdensity of galaxies, independent of optical brightness or survey depth. Second, when it existed. The Sloan Great Wall is relatively nearby in cosmic terms. The Hercules Corona Borealis Great Wall existed when the universe was less than a third of its current age. Structure formation should have been less advanced, not more. This timing makes the size of the wall vastly more difficult to explain. Gravity simply had less time to act. There are also other proposed extreme structures, such as the giant GRB ring, reported in 2015. This apparent ring-like arrangement of gamma-ray bursts spans several billion light-years in diameter. However, its interpretation remains controversial. Many astronomers argue that it is more likely a statistical artifact or a projection effect rather than a true physical structure. The Hercules Corona Borealis Great Wall, by contrast, shows stronger statistical significance and spatial coherence. What distinguishes the Great Wall is not just that it is large, but that it is coherent, early, and persistent across independent analyses. It is not easily dismissed as a byproduct of how data is sliced or visualized. Multiple statistical tests indicate that its galaxy density exceeds background expectations by a wide margin. Another important distinction lies in dimensionality. Many large structures are filamentary, long thread-like chains of galaxies. The Hercules Corona Borealis Great Wall appears more sheet-like, a two-dimensional surface extending across space. This geometry makes it harder to explain as a chance alignment of smaller features. In simulations of large-scale structure, walls do form, but not at this scale and not this early. Filaments merge. Sheets emerge at the boundaries of voids. But these features are limited by the same growth constraints imposed by cosmic expansion and finite time. The Great Wall pushes well beyond those simulated outcomes. Taken together, these comparisons reveal something crucial. This is not just another large structure. It occupies a different category altogether. Earlier discoveries stretched theory. This one strains it. That does not mean cosmology has failed. It means cosmology has encountered a boundary condition, an extreme case that tests whether our assumptions are truly universal or merely typical. If the Great Wall were one of many similar structures, the cosmological principle would be in serious jeopardy. But if it remains rare, perhaps one of only a handful across the observable universe, then it may represent the tail end of a statistical distribution rather than a contradiction of physical law. Yet rarity alone does not erase its implications. Even a single structure can reveal missing physics if it lies beyond what current models naturally produce. The Hercules Corona Borealis Great Wall therefore stands apart from its predecessors. Not because it is the first big structure we've seen, but because it may be the first that truly forces us to ask whether the largest patterns in the universe are governed by limits we have underestimated. In the next chapter, we move deeper into the mathematics of structure formation itself, examining why gravity struggles to build something this large, and what that struggle reveals about time, expansion, and the deep architecture of the cosmos. Chapter 8. Why gravity should not be able to build something this large. To understand why the Hercules Corona Borealis Great Wall presents such a serious problem for cosmology, it is necessary to examine the mechanics of structure formation in detail. The issue is not philosophical or observational. It is mathematical. According to established models, gravity simply should not have had enough time to assemble a coherent structure on this scale. All large-scale cosmic structure grows from tiny initial irregularities. In the early universe, matter was distributed with extraordinary uniformity. Measurements of the cosmic microwave background show that density variations were only about 1 part in 100,000. These small fluctuations are the seeds from which all galaxies, clusters, filaments, and walls eventually formed. Gravity amplifies these fluctuations, but it does so slowly. The growth rate of structure is governed by a balance between gravitational attraction and cosmic expansion. Gravity pulls matter together. Expansion stretches space itself, increasing the distances between regions of matter. In the early universe, expansion was rapid, working directly against gravitational collapse. Even though matter density was higher than it is today, gravity still faced strong resistance from expansion. This balance places a strict upper limit on how quickly structures can grow. Cosmological models track this growth using linear perturbation theory at early times and nonlinear simulations at later times. These calculations consistently show that structures form hierarchically. Small objects collapse first. Larger structures emerge later as smaller ones merge and accrete matter over billions of years. The critical point is scale. The farther apart two regions of matter are, the longer gravity takes to pull them into a coherent structure. On distances of hundreds of millions of light years, the timescale for gravitational coordination becomes comparable to the age of the universe itself. Beyond that, gravity simply does not have time to act. This leads to the concept of a maximum structure size. Depending on assumptions about cosmological parameters, this scale lies between roughly 300 and 400 million light-years. Beyond this scale, matter distributions should average out, and coherent overdensities should dissolve into statistical noise rather than persist as identifiable structures. The Hercules Corona Borealis Great Wall exceeds this limit by a wide margin. Its longest dimension approaches 1.4 billion light-years, more than 3 times the expected maximum. This is not a marginal violation, it is a substantial one. The timing makes the problem even sharper. The light we observe from this structure was emitted when the universe was only about 3.8 billion years old. At that epoch, structure formation was still in an early phase. Many galaxies were still assembling, clusters were incomplete, filaments were still developing. Yet this wall was already present. To appreciate why this is difficult to explain, consider how density fluctuations grow mathematically. Growth is proportional to the scale factor of the universe during matter-dominated eras. Even under ideal conditions, the amplification of density contrasts is modest over the first few billion years. Starting from tiny initial fluctuations, there simply is not enough time to reach the levels of overdensity required to define such a massive structure across such distances. Dark matter helps, but it does not solve the problem outright. Dark matter began collapsing earlier than normal matter because it did not interact with radiation. This allowed it to form gravitational scaffolding sooner. Galaxies later formed within these dark matter halos. However, dark matter obeys the same gravitational laws and faces the same expansion-driven constraints. It accelerates structure formation, but it does not eliminate time limits. Numerical simulations reinforce this conclusion. When cosmologists simulate the evolution of the universe using initial conditions consistent with observations, structures resembling the cosmic web emerge naturally. Filaments, clusters, and walls form. But even the largest simulated structures fall short of the scale implied by the Great Wall, especially at early cosmic times. This discrepancy is not a failure of simulation resolution or computational power. It reflects fundamental constraints built into the equations themselves. The combination of initial density fluctuations, gravitational growth rates, and cosmic expansion produces a predictable envelope of structure sizes. The Hercules Corona Borealis Great Wall lies outside that envelope. One might argue that the wall is not truly gravitationally bound as a single entity. This is partially correct. It is not a solid object in the classical sense, but coherence does not require binding. The issue is not whether the wall will collapse into a single object, but whether it could emerge as a statistically significant overdensity at all. Even loosely connected structures require coordinated growth across large distances. The regions forming the wall must share a common overdensity history. That coordination should have been erased by expansion and averaging effects at this scale. This brings the discussion back to the cosmological principle. Homogeneity on large scales is not an abstract assumption. It arises naturally from inflation and the finite speed at which information and gravitational influence propagate. Beyond a certain distance, regions of the universe simply cannot know about each other well enough to evolve coherently. The Great Wall appears to violate this expectation. It suggests that matter across vast distances evolved in a correlated way earlier than theory allows. That correlation is the heart of the problem. Importantly, this does not imply that gravity behaves incorrectly. It implies that either the initial conditions contained unusually large fluctuations, or that our understanding of how those fluctuations evolve is incomplete. The equations work. The boundary conditions may not. This distinction matters. Physics does not break at the wall. Instead, the wall exposes where assumptions become strained. It forces cosmology to confront the rare but consequential possibility that the early universe contained structures seeded at scales larger than usually considered. In the next chapter, this possibility will be examined more closely by turning to the origin of those initial conditions themselves. If gravity could not build the wall from typical fluctuations, then the explanation must lie deeper, within the physics of inflation and the primordial universe that set the stage for everything that followed. Chapter 9: Inflation, Primordial Fluctuations, and the Question of an Unfair Head Start. If gravity could not have built the Hercules Corona Borealis Great Wall fast enough under normal conditions, then the only remaining place to look is the beginning itself. Long before galaxies existed, long before atoms formed, the universe passed through a brief but decisive phase that determined how all later structure would unfold. That phase is known as cosmic inflation, and it is the most likely place where a structure like this could have gained an impossible advantage. Inflation describes a period of extremely rapid expansion that occurred fractions of a second after the Big Bang. During this epoch, space itself expanded exponentially, increasing in size by an enormous factor in a vanishingly small amount of time. Inflation was introduced to solve several fundamental problems in cosmology, including why the universe appears so uniform and why distant regions share similar physical properties. Crucially, inflation also explains the origin of the tiny density fluctuations that later grew into galaxies and cosmic structure. These fluctuations were not classical irregularities. They were quantum in nature. At microscopic scales, quantum fields naturally fluctuate. Inflation took those microscopic fluctuations and stretched them to macroscopic, even cosmic scales. This process seeded the universe with a spectrum of density variations. Most of them were extremely small, consistent with what we observe in the cosmic microwave background. However, quantum processes are inherently probabilistic. While most fluctuations cluster around an average value, rare outliers are unavoidable. Inflation does not produce a perfectly uniform pattern. It produces a statistical distribution. The key question is whether inflation could have produced a fluctuation large enough over a large enough region to later manifest as the Hercules Corona Borealis Great Wall. If such a region began with a higher than average density contrast, it would have started gravitational collapse earlier and progressed faster than surrounding regions. This would amount to a cosmic head start. Gravity would not need to act across the full 1.4 billion light-year scale. Instead, matter across that region would already share a correlated overdensity from the very beginning. Structure formation would then proceed locally within a region that was predisposed to coherence. In principle, this is allowed by inflationary theory. The equations governing inflation do not forbid rare, large-scale fluctuations. What they constrain is frequency. Extremely large fluctuations should be exceedingly rare. The universe should be mostly smooth, with only occasional regions deviating significantly from the average. The challenge is determining whether the Great Wall falls within the realm of rare but possible or crosses into effectively impossible. This distinction depends sensitively on the inflationary model used. Different models predict different fluctuation spectra. Some allow slightly enhanced power at large scales. Others suppress it more strongly. Current observations of the cosmic microwave background place strong limits on large-scale fluctuations, but those limits are statistical rather than absolute. The CMB provides only one realization of the universe. Cosmic variance, the fact that we observe only a single universe, limits how precisely we can constrain the tails of the fluctuation distribution. This leaves room for interpretation. A structure like the Great Wall could represent a rare statistical outlier rather than a failure of inflation itself. In a universe as large as ours, even extremely improbable events can occur at least once. However, there is an important nuance. Inflation stretches fluctuations beyond the causal horizon, meaning that regions separated by vast distances can share correlated initial conditions. This mechanism explains why the universe appears uniform on large scales. It also provides a pathway for creating correlations that later appear impossible under standard gravitational growth alone. If the Great Wall originates from such a correlated region, then its size is not determined by post-inflationary physics alone. Its scale would be inherited directly from inflation. Gravity would merely sculpt what inflation already imprinted. This interpretation preserves the cosmological principle in a statistical sense. The universe remains homogeneous on average, but rare deviations are permitted. The principle becomes probabilistic rather than absolute. Yet this explanation introduces discomfort of its own. If inflation allows fluctuations this large, why do we not see more structures approaching this scale? Why are such walls so rare? Why do most regions conform neatly to theoretical expectations, while a few stretch them to the breaking point? One possible answer lies in observational bias. Large structures are easier to detect than smaller ones at great distances. They stand out statistically, but this cannot fully explain their scarcity. Even accounting for detection limits, structures of this scale appear exceptional. Another possibility is that inflation itself was not perfectly uniform. Some models allow spatial variation in inflationary parameters. In these scenarios, different regions of the universe experience slightly different inflationary histories. This could produce localized enhancements in fluctuation amplitude without disrupting global uniformity. Such models remain speculative, but they are actively studied. The Great Wall provides a rare observational anchor for testing them. It transforms inflation from an abstract early universe mechanism into a testable source of cosmic anomalies. Importantly, none of this implies that inflation is wrong. On the contrary, inflation remains the most successful framework for explaining early universe conditions. The issue is whether our simplest versions of it capture the full complexity of what occurred. The Hercules Corona Borealis Great Wall may represent a boundary case, a structure formed not by ordinary gravitational evolution, but by extraordinary initial conditions. If so, it offers a glimpse into the extremes of inflationary physics rather than a refutation of cosmology. In the next chapter, this discussion will be grounded further by examining whether the Great Wall is truly a single coherent structure or a statistical assembly of smaller components. If its unity dissolves under closer scrutiny, the theoretical tension may ease. If it remains intact, the implications for inflation become even more profound. Chapter 10. 1. Structure or many. The problem of defining coherence at extreme scale. Before deciding whether the Hercules Corona Borealis Great Wall truly challenges cosmology, astronomers must confront a deceptively simple question. Is it actually one structure? At smaller scales, identifying a galaxy or a cluster is relatively straightforward. Gravity binds the system, its boundaries are reasonably well defined, and its internal motions are coherent. At scales approaching 1 billion light-years, those criteria become difficult to apply. What appears as a single entity may instead be an alignment of smaller structures viewed through a limited observational lens. The Great Wall is not a solid object. It is not gravitationally bound as a whole, nor does it behave as a single dynamical system. Its identification relies on statistical overdensity rather than direct physical cohesion. This makes the concept of structure inherently ambiguous at these scales. Astronomers must decide how much clustering is required before a region is labeled a coherent feature rather than a coincidental pattern. The original detection relied on gamma-ray burst locations, which act as tracers of star-forming galaxies. When those bursts were plotted in three-dimensional space, a significant concentration appeared in a particular region of the sky, and at similar redshifts. The spatial correlation exceeded what would be expected from random distribution. That correlation is real. The challenge lies in interpreting what it represents. One possibility is that the Great Wall is a contiguous sheet of galaxies formed within a single overdense region. In this case, its size reflects a genuine large-scale feature imprinted early in cosmic history. Another possibility is that it consists of multiple filaments and clusters that happen to align across a narrow redshift range, producing the illusion of a continuous wall when viewed statistically. Distinguishing between these interpretations requires careful definition of boundaries. There is no natural edge where galaxy density abruptly drops to zero. Instead, density decreases gradually. Any size estimate depends on choosing a threshold. How much overdensity qualifies as inside the structure versus outside it. Adjusting that threshold changes the measured dimensions. Critics of the Great Wall's significance argue that its quoted 1.4 billion light-year size may reflect generous boundary choices. Using stricter definitions could break it into smaller components, each more consistent with theoretical expectations. From this perspective, the structure may be impressive, but not fundamentally problematic. Supporters counter that even conservative definitions leave an object far larger than expected. Regardless of how boundaries are drawn, the overdensity extends across an enormous region. The continuity of galaxy concentration is not easily dismissed as chance alignment. Moreover, similar analyses applied elsewhere in the sky do not routinely produce structures of comparable scale. Another line of investigation focuses on connectivity. In the cosmic web, filaments connect clusters in branching networks. At what point does a network of connected filaments become a single structure? If coherence is defined by connectivity alone, then the universe contains structures spanning vast distances. However, cosmological theory predicts that such connectivity should lose statistical significance beyond a certain scale. To test this, astronomers analyze correlation functions and percolation thresholds. These tools quantify how clustering strength changes with scale. Studies of the Great Wall show enhanced correlation across its extent, but not uniformly. Some regions are denser than others. The wall is not homogeneous. It is a patchwork of overdense regions connected by lower density bridges. This internal variation complicates interpretation. It suggests the Great Wall is not a monolithic feature, but a collection of substructures linked by the cosmic web. The question becomes whether this linkage is meaningful or coincidental. At smaller scales, similar ambiguity exists, but the statistical separation between structure and noise is clearer. Distance uncertainties also play a role. Redshift measurements for gamma-ray bursts and distant galaxies carry errors. Small uncertainties along the line of sight can smear distinct structures into apparent continuity. While this effect is accounted for in analyses, it cannot be eliminated entirely. Projection effects further complicate matters. Even in three-dimensional mapping, observational selection biases influence which galaxies are included. Regions with higher star formation are overrepresented because they produce more detectable gamma-ray bursts. This could artificially enhance perceived connectivity. Despite these caveats, the Great Wall persists across multiple datasets and methods. It is not an artifact of a single survey or analysis technique. Independent studies using different tracers have identified similar overdensities in the same region of space. While details vary, the large-scale feature remains. This places cosmologists in an uncomfortable position. If the Great Wall is treated as a single structure, it strains theoretical limits. If it is treated as a coincidental assembly, its statistical significance must be explained. Either way, the phenomenon demands attention. The broader issue is that cosmology lacks a universally agreed-upon definition of structure at extreme scales. The transition from meaningful coherence to statistical fluctuation is gradual, not sharp. The Great Wall sits precisely in this grey zone. Rather than resolving the problem, this ambiguity reframes it. The Great Wall may not be a violation of physics in the traditional sense. It may instead expose the limits of how structure is defined and measured. The challenge may lie not in the universe itself, but in the conceptual tools used to describe it. In the next chapter, attention will shift from definition to consequence. Regardless of how the Great Wall is classified, its existence influences how matter, dark matter, and expansion interacted in the early universe. Understanding those interactions is essential for evaluating whether this structure represents a statistical anomaly or a genuine signal of new physics. Chapter 11: Dark Matter, Growth Rates, and the Speed Limit of Cosmic Structure. Whether the Hercules Corona Borealis Great Wall is treated as a single structure or an interconnected assembly, its existence forces attention toward the engine of large-scale growth: dark matter. Ordinary matter alone cannot account for the speed or scale at which cosmic structures form. Gas pressure, radiation, and thermal motion resist collapse. Dark matter, by contrast, interacts almost exclusively through gravity. It provides the scaffolding on which galaxies assemble. Any explanation for an extreme structure must therefore confront how dark matter behaves under early universe conditions. In the standard cosmological model, dark matter is cold. Its particles move slowly compared to the speed of light, allowing density perturbations to grow efficiently. After inflation ended and the universe cooled, dark matter began collapsing into halos and filaments long before normal matter could follow. Baryonic matter remained coupled to radiation until recombination, delaying its collapse. When it finally decoupled, it fell into pre-existing dark matter wells. This sequence explains why galaxies trace the cosmic web so faithfully. However, even cold dark matter imposes limits. Growth proceeds hierarchically. Small overdensities collapse first. Larger structures emerge only as smaller ones merge or accrete additional matter. This process takes time. The expansion of the universe competes with gravity, stretching distances and slowing collapse on large scales. The combined effect sets a practical upper bound on how quickly coherence can develop across vast regions. For a structure observed when the universe was only a few billion years old, the timeline is tight. To span over 1 billion light-years, matter across that region would need to share correlated motion early on. Dark matter alone cannot communicate gravitational influence faster than light, nor can it organize itself instantaneously. This places a fundamental constraint on growth rates. One way around this constraint is enhanced initial conditions. If dark matter density was already elevated across a large region at early times, collapse could proceed in parallel rather than sequentially. In this case, gravity would not need to act across the full extent. Each subregion would evolve locally but coherently, producing an extended structure without violating causality. Another possibility involves modifications to dark matter properties. While cold dark matter is the simplest assumption, alternatives exist. Warm dark matter, consisting of faster-moving particles, suppresses small-scale structure, but can smooth distributions on larger scales. This generally works against forming large coherent walls, making it an unlikely solution. Self-interacting dark matter introduces additional forces within the dark sector. If dark matter particles exchange momentum through collisions, they could redistribute energy and density differently from collisionless models. In principle, this might enhance large-scale coherence under specific conditions. However, constraints from galaxy clusters and gravitational lensing strongly limit how strong such interactions can be. More exotic models consider multiple dark matter components or time-varying properties. In these frameworks, dark matter behavior in the early universe may differ from its behavior today. Temporary enhancements in clustering efficiency could allow unusually rapid growth, leaving behind rare large structures as fossils of that phase. These ideas remain speculative, but are actively explored because they preserve much of standard cosmology while addressing anomalies. Another factor is bias. Galaxies do not trace dark matter perfectly. Regions of slightly higher dark matter density can host disproportionately more luminous galaxies or star formation, making structures appear more prominent than the underlying mass distribution. The Great Wall may therefore represent a moderate dark matter overdensity, amplified by observational traces. Simulations help clarify these possibilities. Large cosmological simulations incorporating cold dark matter reproduce filaments and walls remarkably well, but structures as large as the Great Wall are rare. When they do appear, they often arise from atypical initial conditions rather than altered physics. This supports the interpretation of the Great Wall as a statistical extreme rather than a fundamental failure. Yet rarity alone does not eliminate tension. If simulations consistently underproduce such structures compared to observations, the discrepancy must be addressed. Improving statistics requires larger simulation volumes and more precise observational catalogues. Both are currently advancing, narrowing uncertainty. Dark matter, therefore, sits at the center of the debate. It does not provide an obvious escape from the growth rate problem, but it offers pathways for reinterpretation. Either the Great Wall reflects an unlikely but permissible realization within standard dark matter cosmology, or it hints at complexity in the dark sector not yet captured by current models. The next chapter will extend this analysis by examining the role of cosmic expansion and dark energy. Growth rates are shaped not only by gravity and initial density, but also by how rapidly space itself expands. Understanding that balance is essential for evaluating whether the Great Wall represents an anomaly of matter or of cosmic dynamics. Chapter 12: Expansion, Dark Energy, and the Timing Problem. If dark matter governs where structure forms, cosmic expansion governs whether it can form at all. Gravity pulls matter together, but expansion stretches space, increasing distances and weakening gravitational influence over time. The balance between these two effects sets a cosmic speed limit on structure formation. For the Hercules Corona Borealis Great Wall, that balance appears unusually strained. In the early universe, expansion was rapid but decelerating. Matter dominated the energy budget, and gravity was strong enough to overcome expansion on many scales. This allowed overdense regions to collapse and grow into the filaments and clusters that define the cosmic web. However, this process was not unlimited. As structures grew larger, the expansion of space increasingly worked against coherence, especially across distances approaching hundreds of millions of light years. Dark energy complicates this picture further. Although it became dominant only several billion years after the Big Bang, its influence was not zero before that transition. Even a small contribution from dark energy alters the expansion history, subtly reducing the time available for gravity to organize matter on the largest scales. This means that early structure formation already faced a narrowing window. For a structure observed when the universe was roughly a quarter of its current age, the timing problem becomes acute. The Great Wall had to begin assembling early, continue growing efficiently, and avoid being pulled apart by expansion. This requires not only favorable initial conditions, but also an expansion history that did not excessively suppress growth in that region. Standard cosmological models account for this balance and predict a characteristic scale beyond which coherence should fade. That scale is not sharply defined, but it emerges consistently in simulations and analytic calculations. Structures larger than a few 100 million light-years should lose contrast and dissolve into statistical noise. The Great Wall challenges this expectation by remaining coherent well beyond that range. One possible explanation is that expansion was locally counteracted by enhanced gravitational attraction. A region with higher than average matter density would expand more slowly than the cosmic mean. In effect, it would decouple slightly from global expansion, allowing structure to grow more efficiently within it. This mechanism operates in galaxy clusters and superclusters, but extending it across 1 billion light-years requires extreme conditions. Another possibility is that expansion itself was not perfectly uniform. While the universe is homogeneous on average, small regional variations in expansion rate are allowed. These variations are normally negligible, but in rare cases they could influence structure growth. If the region containing the Great Wall experienced slightly slower expansion early on, gravity would have had more time to act. This idea borders on speculative territory because observational evidence for large-scale expansion anisotropies is limited. Most measurements support isotropy to high precision. However, precision does not imply perfection. Small deviations could exist below current detection thresholds, leaving room for rare anomalies. Dark energy models also introduce flexibility. If dark energy evolved differently in the past, its suppressive effect on growth might have been weaker at early times. This would allow structures to grow larger before acceleration dominated. Current observations constrain dark energy behavior tightly, but they do not eliminate all variation. An additional consideration is that expansion does not act uniformly on all scales at all times. Regions with strong internal gravity can remain dynamically coherent even as the surrounding universe accelerates. While this effect is well understood at cluster scales, extrapolating it to extreme scales tests the boundary between local dynamics and global expansion. The Great Wall exists near this boundary, where the distinction becomes blurred. Importantly, the Great Wall does not require expansion to behave differently everywhere. It requires only one region to experience slightly altered conditions. In a universe of immense size, even highly improbable regional histories can occur once. The expansion problem therefore mirrors the initial fluctuation problem. Both point toward rarity rather than rule-breaking. The universe may permit extreme structures without abandoning its overall statistical regularity. What makes the Great Wall significant is not that it definitively violates cosmology, but that it forces models to operate at their limits. It exposes where assumptions transition from robust averages to fragile extrapolations. In the next chapter, attention will turn to observational strategy. How confident are we in measuring distances, densities, and coherence at such extreme scales? Understanding observational uncertainty is essential before any theoretical revision can be justified. Chapter 13. Observational limits, biases, and the risk of seeing what we expect. Before any structure can challenge theory, its observational foundation must be examined with caution. At distances measured in billions of light-years, every conclusion rests on layers of inference. The Hercules Corona Borealis. Great Wall is not observed directly as a continuous object. It is reconstructed from sparse data, statistical correlations, and models that translate limited signals into three-dimensional structure. Understanding the limits of these methods is essential to evaluating how firmly the Great Wall can be regarded as real, coherent, and physically meaningful. The first constraint is distance itself. At extreme redshifts, astronomers cannot rely on direct geometric measurements. Distances are inferred from redshift, which measures how much the universe has expanded since the light left its source. This process depends on a cosmological model. Small uncertainties in cosmological parameters propagate into large uncertainties in distance at these scales. While modern measurements are precise, they are not exact, and cumulative errors matter when structures approach theoretical size limits. The Great Wall was initially identified using gamma-ray bursts rather than galaxies. Gamma-ray bursts are powerful but rare. They do not sample the universe uniformly. They trace specific astrophysical events linked to massive stars or compact object mergers. This introduces selection bias. Regions with higher star formation rates produce more gamma-ray bursts and are therefore more likely to be highlighted in burst-based surveys. An apparent overdensity of bursts may exaggerate the prominence of underlying galaxy concentrations. Sampling bias is compounded by small number statistics. The number of gamma-ray bursts used to identify the structure is limited. When sample sizes are small, random clustering can appear more significant than it truly is. Statistical techniques attempt to account for this, but uncertainty remains. The distinction between a rare fluctuation and a genuine structure becomes blurred when the dataset itself is sparse. Foreground and background contamination also affect interpretation. Even when redshift information is available, uncertainties along the line of sight can smear separate structures into apparent continuity. Two unrelated overdensities at slightly different distances can appear connected when projected into a three-dimensional map with finite resolution. At extreme distances, this effect becomes harder to control. Galaxy surveys face related challenges. Detecting faint galaxies at high redshift requires long exposures and careful calibration. Observational limits mean that only the brightest galaxies are included. Fainter members of the structure may go undetected, distorting perceived density and shape. Regions with slightly brighter galaxy populations may appear artificially enhanced relative to equally massive but fainter regions. Survey geometry introduces additional bias. Observational programs do not sample the sky uniformly. Coverage varies by direction, depth, and wavelength. Some regions are studied extensively, while others remain poorly explored. Large structures are more likely to be detected in well-sampled regions, creating an uneven census of extreme features. Data processing choices also influence results. The algorithms used to identify overdensities depend on smoothing scales, threshold definitions, and clustering criteria. Adjusting these parameters can change whether a feature appears continuous or fragmented. While such choices are guided by physical reasoning, they are not uniquely determined. Different teams using different methods may arrive at different characterizations of the same data. Confirmation across independent datasets mitigates some concerns, but it does not eliminate them entirely. The Great Wall has been identified using multiple approaches, which strengthens confidence in its existence. However, consistency does not guarantee accuracy. Independent analyses can share underlying assumptions, including cosmological parameters and statistical frameworks. Human perception plays a subtle role as well. Large-scale maps invite pattern recognition. Astronomers are trained to guard against this, but the risk remains. Once a structure is proposed, subsequent analyses may unconsciously frame results in ways that emphasize coherence rather than fragmentation. This is not misconduct, but a known cognitive bias in data interpretation. None of these limitations imply that the Great Wall is an illusion. They indicate that its precise size, shape, and degree of coherence remain uncertain. The difference between a structure that is slightly too large and one that is dramatically too large matters greatly for theory. Resolving that difference requires better data. Future observations will reduce these uncertainties. Larger galaxy surveys with uniform sky coverage will provide denser sampling. Improved redshift measurements will sharpen distance estimates. Cross-correlation between different traces, including galaxies, quasars, and absorption features, will provide independent checks on coherence. The James Webb Space Telescope and next-generation ground-based surveys will not directly image the entire Great Wall, but they will refine understanding of its constituent galaxies. Their properties will reveal whether these galaxies share common formation histories or merely occupy similar regions of space. Until then, caution is warranted. The Great Wall occupies a regime where observational limits and theoretical expectations overlap. It may represent a genuine boundary case, or it may shrink under improved scrutiny. Either outcome is informative. The role of observation here is not to provide certainty, but to define confidence. The Great Wall remains a compelling feature, But its challenge to cosmology must be weighed against the limitations inherent in observing the universe at its most extreme scales. In the next chapter, the focus will shift from observation to simulation. If such structures can arise naturally in Chapter 15, do alternative cosmologies explain extreme structures better? When a structure appears to strain the limits of the standard cosmological model, it is natural to ask whether alternative frameworks provide a more comfortable explanation. The Hercules Corona Borealis Great Wall has prompted renewed interest in models that modify assumptions about initial conditions, cosmic expansion, or the nature of gravity itself. Evaluating these alternatives requires careful separation of explanatory power from added complexity. One class of alternatives modifies the statistical properties of the early universe. The standard model assumes that primordial density fluctuations were nearly Gaussian, meaning extreme deviations were rare. Some inflationary models allow for non-Gaussian fluctuations, increasing the likelihood of large correlated regions. In such scenarios, structures as large as the Great Wall become less improbable. However, these models must still match precise observations of the cosmic microwave background, which tightly constrain allowable deviations. Current data leave limited room for significant non-Gaussianity. Another approach alters the nature of dark matter. Warm dark matter models, for example, suppress small-scale structure while leaving large-scale correlations relatively intact. This can change the appearance of the cosmic web, producing smoother but more extended features. However, these models often struggle to reproduce the observed abundance of small galaxies, creating tension with well-established observations closer to home. Modified gravity theories represent a more radical departure. By changing how gravity behaves on large scales, these models can alter the growth rate of structure. Some predict enhanced clustering over vast distances. Yet they face strong constraints from galaxy rotation curves, gravitational lensing, and large-scale velocity fields. Any modification that explains one anomaly must also remain consistent with many independent lines of evidence. There are also models that relax the assumption of global homogeneity without abandoning it entirely. In these frameworks, the universe is statistically homogeneous, but allows for larger than expected regional variations. This perspective reframes extreme structures as manifestations of cosmic variance, rather than violations of principle. While conceptually appealing, such models often lack unique predictions that distinguish them clearly from the standard picture. Importantly, alternative cosmologies introduce additional parameters. Each new parameter increases flexibility but reduces predictive power, a model that can explain any observation risks explaining none. For this reason, cosmologists apply a high threshold when considering departures from the standard model. Extraordinary claims require not only explanation, but necessity. At present, no alternative cosmology provides a decisive advantage in explaining the Great Wall. Most can accommodate it under certain assumptions, but none predict it as a natural outcome without tuning. In contrast, the standard model already allows rare, extreme structures within its statistical framework, albeit at low probability. This comparison highlights a recurring theme in cosmology. Observations at the edge of detectability often test the tails of distributions rather than the core of theory. When a feature lies at the extreme but remains statistically allowed, the burden of proof for radical revision remains high. The Great Wall therefore occupies an ambiguous position. It may represent a rare but permissible outcome of known physics, or it may hint at subtle departures that current data cannot yet resolve. Alternative models remain tools for exploration rather than replacements. The next chapter will shift focus from theory to implication. Regardless of its ultimate explanation, the existence of such a large structure forces reconsideration of how cosmologists interpret scale, rarity, and expectation in an effectively infinite universe. Large numerical universes, then their existence may be surprising, but not forbidden. Chapter 14. What simulations say about structures this large. Once observational limits are acknowledged, the next question becomes whether structures on the scale implied by the Hercules Corona Borealis Great Wall can arise within accepted cosmological models. This question cannot be answered through observation alone. It requires numerical simulations that evolve the universe forward from its earliest conditions, tracking how matter clusters over billions of years under known physical laws. These simulations provide a controlled environment in which the plausibility of extreme structures can be tested. Modern cosmological simulations begin with initial conditions derived from measurements of the cosmic microwave background. These measurements encode tiny density fluctuations present when the universe was only a few 100,000 years old. Under the Standard Model, these fluctuations are nearly scale invariant and Gaussian, meaning that large deviations are rare but not forbidden. Gravity amplifies these fluctuations over time, causing matter to collapse into filaments, sheets, and nodes that define the cosmic web. In simulations, structure formation proceeds hierarchically. Small overdensities collapse first, merging into larger systems as time progresses. Galaxy clusters form at the intersections of filaments, while voids expand between them. This process naturally produces large-scale patterns, but the coherence of these patterns is limited by the size of the simulation volume and the statistical properties of the initial fluctuations. Early simulations were constrained by computational limits. Their volumes were often too small to capture the rarest fluctuations. As a result, they appeared to impose an upper bound on structure size that aligned comfortably with theoretical expectations. However, as computing power increased, simulation volumes expanded dramatically. New generations of simulations encompass volumes comparable to or exceeding the observable universe, allowing rare events to emerge statistically. In these larger simulations, structures approaching gigaparsec scales do appear, though infrequently. They are not uniform objects, but extended alignments of filaments and clusters that span enormous distances. Importantly, these structures are not gravitationally bound as a whole. Their coherence arises from correlated initial conditions rather than ongoing interaction across their full extent. This distinction matters. The cosmological principle constrains large-scale uniformity, not the existence of extended correlations. Simulations show that while matter becomes homogeneous on average, local deviations can persist across vast distances. These deviations are unlikely, but their probability is non-zero. When simulation volumes are large enough, improbable configurations become inevitable. The Hercules Corona Borealis Great Wall, if real, may represent such a statistical outlier. Its apparent size would place it at the extreme tail of the distribution rather than outside it. Simulations suggest that defining a strict maximum structure size is misleading. Instead, structure size follows a probability distribution with a long tail. However, simulations also reveal important caveats. The apparent size of a structure depends strongly on how it is defined. Changing the criteria for connectivity, density thresholds, or smoothing scales can fragment a large feature into smaller components. What appears as a single wall under one definition may break into multiple independent structures under another. This sensitivity complicates direct comparison between simulations and observations. Observational data are incomplete and noisy, while simulations provide full information by construction. Bridging this gap requires mock observations that apply the same selection effects and biases to simulated universes as exist in real surveys. When this is done, simulated structures can appear larger and more coherent than they truly are in three-dimensional space. Another factor is cosmic variance. The observable universe represents only one realization of the underlying statistical process. Simulations generate many realizations. In some, extreme structures appear. In others, they do not. The existence of a single extreme feature in our universe does not invalidate the model if its probability is low, but non-zero. Importantly, simulations do not predict that such structures should be common. they remain rare. This rarity aligns with the fact that few candidates comparable to the Great Wall have been identified. The absence of numerous similar structures supports the idea that these are exceptional rather than representative features. At the same time, simulations highlight the limitations of intuition. Human expectations about scale are often shaped by familiar astrophysical objects. When extrapolated to cosmological volumes, those intuitions break down. The universe is vast enough that structures spanning billions of light years, while astonishing, may still arise from random initial conditions. Simulations therefore neither fully endorse nor reject the existence of the Great Wall. They show that the standard model can accommodate extreme correlations under specific circumstances. Whether the observed structure fits within those circumstances remains an open question. The value of simulations lies not in providing definitive answers, but in mapping what is possible. They define the boundaries of plausibility. Within those boundaries, observation must determine which configurations nature has realized. The next chapter will examine whether alternative cosmological models offer cleaner explanations for such large-scale features, or whether they introduce new problems of their own. Chapter 15. Do alternative cosmologies explain extreme structures better? When a structure appears to strain the limits of the standard cosmological model, it is natural to ask whether alternative frameworks provide a more comfortable explanation. The Hercules Corona Borealis. Great Wall has prompted renewed interest in models that modify assumptions about initial conditions, cosmic expansion, or the nature of gravity itself. Evaluating these alternatives requires careful separation of explanatory power from added complexity. One class of alternatives modifies the statistical properties of the early universe. The standard model assumes that primordial density fluctuations were nearly Gaussian, meaning extreme deviations were rare. Some inflationary models allow for non-Gaussian fluctuations, increasing the likelihood of large correlated regions. In such scenarios, structures as large as the Great Wall become less improbable. However, these models must still match precise observations of the cosmic microwave background, which tightly constrain allowable deviations. Current data leave limited room for significant non-Gaussianity. Another approach alters the nature of dark matter. Warm dark matter models, for example, suppress small-scale structure while leaving large-scale correlations relatively intact. This can change the appearance of the cosmic web, producing smoother but more extended features. However, these models often struggle to reproduce the observed abundance of small galaxies, creating tension with well-established observations closer to home. Modified gravity theories represent a more radical departure. By changing how gravity behaves on large scales, these models can alter the growth rate of structure. Some predict enhanced clustering over vast distances. Yet they face strong constraints from galaxy rotation curves, gravitational lensing, and large-scale velocity fields. Any modification that explains one anomaly must also remain consistent with many independent lines of evidence. There are also models that relax the assumption of global homogeneity without abandoning it entirely. In these frameworks, the universe is statistically homogeneous, but allows for larger than expected regional variations. This perspective reframes extreme structures as manifestations of cosmic variance rather than violations of principle. While conceptually appealing, such models often lack unique predictions that distinguish them clearly from the standard picture. Importantly, alternative cosmologies introduce additional parameters. Each new parameter increases flexibility but reduces predictive power. A model that can explain any observation risks explaining none. For this reason, cosmologists apply a high threshold when considering departures from the standard model. Extraordinary claims require not only explanation, but necessity. At present, no alternative cosmology provides a decisive advantage in explaining the Great Wall. Most can accommodate it under certain assumptions, but none predict it as a natural outcome without tuning. In contrast, the standard model already allows rare extreme structures within its statistical framework, albeit at low probability. This comparison highlights a recurring theme in cosmology. Observations at the edge of detectability often test the tails of distributions rather than the core of theory. When a feature lies at the extreme but remains statistically allowed, the burden of proof for radical revision remains high. The Great Wall therefore occupies an ambiguous position. It may represent a rare but permissible outcome of known physics, or it may hint at subtle departures that current data cannot yet resolve. Alternative models remain tools for exploration rather than replacements. The next chapter will shift focus from theory to implication. Regardless of its ultimate explanation, the existence of such a large structure forces reconsideration of how cosmologists interpret scale, rarity, and expectation in an effectively infinite universe. Chapter 16. Rarity, Cosmic Variance, and the Meaning of Too Big. When cosmologists describe a structure as too big, they are rarely making an absolute claim. Instead, they are speaking in the language of probability. The universe does not forbid extreme outcomes outright. It assigns them likelihoods. Understanding the Hercules corona, Borealis Great Wall, therefore requires grappling with a subtle but essential concept: cosmic variance. Cosmic variance refers to the unavoidable statistical uncertainty that arises because we can observe only one universe. Even if the underlying physical laws are perfectly known, the specific realization we inhabit may include rare extremes. Just as a single roll of dice can occasionally produce an unlikely sequence, the universe can generate structures that sit far out on the tail of an otherwise well-behaved distribution. In simulations of large-scale structure, most realizations produce maximum coherent features well below 1 billion light-years. Yet a small fraction generate unusually large walls or filaments. These outcomes are uncommon, but they are not impossible. The crucial question is whether the Great Wall lies within that extreme tail or beyond it. Current analyses suggest it occupies a deeply unlikely region, but still one that remains statistically allowed. The problem is compounded by how structure size is defined. Large-scale features do not have sharp edges. Their boundaries depend on density thresholds, smoothing scales, and methodological choices. A structure's quoted size can vary substantially, depending on how conservatively or aggressively those boundaries are drawn. What appears too big under one definition may appear merely very large under another. Selection effects also play a role. Surveys are more likely to detect the most dramatic structures, especially at great distances where only the brightest traces are visible. Gamma-ray bursts, which helped reveal the Great Wall, preferentially trace massive star-forming galaxies. This introduces bias toward regions of unusually high activity, amplifying apparent coherence. Another factor is the sheer scale of the observable universe. With billions of cubic gigaparsecs to sample, even events with extremely low probability may occur at least once. The discovery of a single extraordinary structure does not necessarily indicate a breakdown of theory. It may simply reflect the inevitability of extremes in a vast system. This reframes the phrase "breaks physics." The Great Wall does not violate known laws in the way an object exceeding the speed of light would. Instead, it challenges expectations about frequency and scale. It tests whether our statistical models fully capture the range of possible outcomes. Cosmology often advances at these margins. The most informative observations are not the typical ones, but the rare outliers that strain interpretation. They force refinement of definitions, deeper statistical analysis, and more careful accounting of uncertainty. In this sense, the Great Wall functions less as a contradiction and more as a calibration point. It marks the boundary between what is common and what is merely possible. The next chapter will examine how future surveys and instruments may determine whether this structure is a singular anomaly or part of a broader population still hidden from view. Chapter 17. The Probability Problem. By the time astronomers accepted that the Hercules Corona Borealis Great Wall was likely real, a deeper and more troubling question emerged. If the structure exists, how probable was its formation in the first place? This question shifts the problem from observation to statistics, from telescopes to mathematics. It asks whether the universe merely produced a rare outcome, or whether our understanding of cosmic probability is incomplete. Cosmology does not forbid unusual structures outright. Instead, it predicts how frequently different structures should occur based on initial conditions in the early universe. These predictions are statistical in nature. The universe began with tiny density fluctuations seeded during inflation that later grew under gravity. Most fluctuations were small, a few were larger. The distribution of these fluctuations follows well-defined statistical rules, usually modeled as Gaussian randomness. In a Gaussian universe, extreme deviations are possible but exponentially rare. Small fluctuations are common. Large ones occur less frequently. Enormous fluctuations are expected to be exceptionally scarce. This statistical framework allows cosmologists to estimate how likely it is for regions of the universe to deviate significantly from average density over large scales. The Hercules Corona Borealis Great Wall appears to represent such a deviation. Its size suggests an overdensity of matter spanning roughly 1.4 billion light-years. For this to arise naturally, the region would have needed an unusually large initial density fluctuation, one far above the cosmic average. The central question becomes whether such a fluctuation is merely rare, or so improbable that it challenges the underlying model. Several studies have attempted to quantify this probability. Using standard cosmological parameters, researchers simulate large volumes of the universe, evolving density fluctuations forward in time under gravity and expansion. They then ask how often structures comparable in size and coherence to the Great Wall appear in these simulations. The answer is uncomfortable. Such structures are not impossible, but they are extremely unlikely. Depending on the exact definition of the structure's boundaries, estimates suggest probabilities ranging from 1 in tens of thousands to 1 in millions. These numbers are not precise. They depend on assumptions about initial conditions, structure definition, and observational thresholds. But even conservative estimates place the Great Wall at the extreme tail of expected outcomes. This does not immediately invalidate the cosmological model. Rare events do occur in large systems. The observable universe is vast, containing trillions of galaxies and enormous volumes of space. With enough opportunities, even unlikely outcomes can happen. This is the logic of cosmic statistics. A 1 in a million event becomes plausible if the universe contains millions of chances for it to occur. However, the problem deepens when considering timing. The Great Wall is observed at a redshift corresponding to a universe only about 3.8 billion years old. At that epoch, structure formation was still underway. The probability calculations are not just about size, but about speed. The structure did not merely form, it formed early. Simulations show that large-scale structures grow gradually. Small density enhancements merge into larger ones over time. The largest structures form last. Finding an enormous structure at such an early cosmic age compresses this timeline, making the event even less probable. It is not just rare in size, but rare in developmental history. One response to this problem is to argue that the structure is not truly coherent. Perhaps it is not a single physical entity, but a chance alignment of smaller structures. If galaxies at different distances happen to line up along our line of sight, the resulting projection could mimic a continuous wall. This explanation would reduce the statistical burden by reclassifying the structure as an observational artifact. Yet multiple analyses argue against this interpretation. The galaxies and gamma-ray bursts associated with the Great Wall occupy a relatively narrow redshift range. They are not scattered randomly along the line of sight. Their spatial distribution shows continuity in 3 dimensions, not merely in projection. This coherence makes the alignment explanation increasingly difficult to sustain. Another approach is to reconsider what counts as a structure. The cosmological principle does not forbid density variations outright. It requires homogeneity only when averaging over sufficiently large volumes. Some researchers argue that the Great Wall does not violate this principle because its density contrast, while extended, is relatively modest. It is large, but not overwhelmingly dense. In this view, the Great Wall represents an extended region of mild overdensity rather than a tightly bound object. Its length is impressive, but its gravitational coherence may be weaker than implied by the term wall. If this interpretation is correct, then the structure may sit closer to the statistical limits of the model without crossing them. However, even under this more forgiving definition, the probability remains low. Large-scale simulations rarely produce features with comparable spatial extent, even when density thresholds are relaxed. The issue is not just how dense the structure is, but how consistently elevated the density remains across such a vast region. This has led some cosmologists to explore modifications to the initial conditions. Inflation is believed to have generated the primordial fluctuations that seeded structure formation. While most models predict nearly Gaussian distributions, slight deviations are possible. Non-Gaussian inflationary models allow for a higher frequency of extreme fluctuations. If the early universe contained more pronounced high-amplitude fluctuations than currently assumed, structures like the Great Wall would become more probable. Importantly, such deviations would leave subtle imprints in the cosmic microwave background. So far, observations strongly constrain these possibilities, but small departures remain allowed. Another possibility involves cosmic variance. We observe only one universe from one location. Statistical predictions apply to ensembles, but we have access to a single realization. It is possible that our observable universe happens to include an unusually large structure simply by chance. This explanation is unsatisfying, but statistically legitimate. Cosmic variance limits how confidently we can assess rarity. We cannot rerun the universe with different random seeds. We can only observe what exists. In that sense, the probability problem may be less about theoretical failure and more about the inherent limitations of inference. Still, the unease remains. The Great Wall is not alone. Other large structures approach or exceed expected limits. While none individually force a revision of cosmology, collectively they form a pattern of tension. Each structure nudges the model toward its breaking point without definitively crossing it. Chapter 17 sits at this uncomfortable intersection, the Hercules corona borealis. Great Wall does not clearly violate cosmological theory, but it resides where the theory becomes strained. Its existence is statistically unlikely, temporally awkward, and structurally extreme. It forces cosmologists to confront whether the tale of the probability distribution is truly understood. The universe may simply be generous with rare events, or it may be signaling that the statistical assumptions we rely on are incomplete. Either way, the probability problem is not a footnote. It is a central challenge posed by the Great Wall, one that pushes cosmology to examine not what is common, but what is barely allowed. Chapter 18: When Assumptions Begin to Crack. The probability problem does not exist in isolation. It leads directly to a more uncomfortable realization: the Hercules corona borealis. Great Wall forces cosmology to confront its deepest assumptions. Not observational techniques, not data quality, but the foundational ideas used to interpret everything we see. At the center of this tension lies a question rarely asked out loud. What if the assumptions we treat as universal truths are only approximations? Modern cosmology rests on a small number of core principles. Among them, none is more central than the cosmological principle. This principle states that when viewed on sufficiently large scales, the universe is homogeneous and isotropic. It has no preferred locations and no preferred directions. This idea is not philosophical decoration. It is the backbone of cosmological equations, models, and simulations. Every major framework describing cosmic evolution assumes this principle. It allows astronomers to simplify the universe mathematically, turning an otherwise impossible problem into something solvable. Without it, the equations governing expansion, structure formation, and cosmic history would become intractably complex. The success of cosmology over the last century is inseparable from this assumption. Yet the Great Wall presses against the scale at which homogeneity is supposed to emerge. Observationally, the universe appears to smooth out when averaged over regions roughly 300 to 400 million light-years across. Beyond that scale, density variations should diminish. Structures should blend into a uniform background. The Great Wall exceeds this scale by a factor of 3 or 4. This does not automatically invalidate the cosmological principle. Homogeneity does not require perfect smoothness, only statistical uniformity. Rare fluctuations can exist without breaking the rule. But the sheer extent of the structure forces cosmologists to ask whether the scale of homogeneity is larger than previously believed, or whether homogeneity is less strict than assumed. If homogeneity emerges only on scales larger than 1 billion light-years, then many conclusions drawn from current models require re-examination. Measurements of matter density, dark energy behavior, and expansion history rely on averaging over assumed homogeneous volumes. If those volumes are not truly representative, systematic biases may exist in our interpretations. This concern extends to simulations. Large-scale cosmological simulations begin with initial conditions based on observed fluctuations in the cosmic microwave background. They assume those fluctuations follow well-defined statistical distributions and evolve under gravity in a uniform expanding space. The resulting cosmic web matches observations remarkably well on most scales. However, simulations rarely produce structures comparable to the Great Wall without fine-tuning. When they do, the structures typically appear later in cosmic time, not when the universe was only a few billion years old. This mismatch suggests either the simulations are missing something subtle, or the structure occupies an extreme corner of parameter space. One possibility is that the universe contains long wavelength modes larger than the observable volume. These modes would represent density variations spanning scales beyond what we can directly measure. If present, they could imprint large coherent patterns onto smaller regions, effectively biasing local structure formation. Such modes are allowed in principle. Inflation could generate fluctuations on scales larger than the observable universe. We would not see these modes directly, but we would feel their influence as large-scale gradients in density. The Great Wall could be a manifestation of such a background fluctuation, not a violation of homogeneity, but a local response to a larger unseen pattern. Another assumption under scrutiny is Gaussianity. Cosmology often assumes that initial density fluctuations follow a Gaussian distribution, meaning extreme deviations are exponentially rare. This assumption is strongly supported by observations of the cosmic microwave background, but it is not absolute. Small deviations from Gaussianity are difficult to detect and easy to overlook. Even slight departures could significantly increase the probability of rare, large-scale structures. If the early universe produced a heavier tail of fluctuations than expected, structures like the Great Wall would become less surprising. This possibility is actively studied, but constrained. Any deviation must be subtle enough to preserve agreement with precision measurements of the early universe. The challenge lies in finding a model that increases the likelihood of rare structures without disrupting everything else that works. Dark matter assumptions also enter the discussion. Most simulations assume cold, collisionless dark matter. This model reproduces small-scale structure well, but its behavior on the larger scales remains indirectly tested. If dark matter possesses weak self-interactions or non-trivial clustering properties, it could alter how large structures grow. Self-interacting dark matter, for example, could enhance coherence across extended regions by redistributing energy and momentum within massive structures. While current constraints limit the strength of such interactions, they do not eliminate them entirely. Subtle effects could accumulate over billions of years. There is also the role of dark energy. Dark energy influences structure formation by accelerating expansion, effectively freezing large-scale growth at late times. If dark energy behaved differently in the early universe, even slightly, it could change the timeline of structure formation. Most models treat dark energy as constant, but alternatives exist where its influence evolves over time. These models remain speculative, but large structures forming earlier than expected could serve as indirect evidence supporting such scenarios. At this stage, no single assumption has been definitively broken. Instead, the Great Wall exposes the cumulative fragility of the framework. Each assumption works well individually. Together, they produce a model that is highly successful but not invulnerable. Cosmology has faced similar moments before. The discovery of cosmic acceleration forced the introduction of dark energy. Flat galaxy rotation curves required dark matter. Each time, observations revealed cracks that could not be ignored. The response was not abandonment of theory, but expansion of it. The Great Wall may represent a similar moment, though less dramatic. It does not demand a revolution, but it invites caution. It reminds cosmologists that assumptions are tools, not truths. They work until they do not, and their limits must be tested, not defended. Importantly, the scientific community has not rushed to rewrite cosmology because of this structure. Instead, it has adopted a posture of tension. The Great Wall is acknowledged as anomalous, studied carefully, and placed within a broader statistical context. This restraint reflects confidence, not denial. If future surveys reveal many more structures of comparable size, the pressure will increase. Patterns matter more than exceptions. A universe filled with billion light-year walls would require fundamental revision. A universe with a few rare extremes may not. For now, Chapter 18 closes with a universe still standing but leaning. The assumptions hold, but they creak under stress. The Great Wall does not shatter cosmology, but it forces cosmologists to listen closely to the sound of strain. The next question is unavoidable. If the assumptions bend but do not break, what does this structure actually represent physically? Is it a meaningful entity, or merely a statistical description imposed on a continuous cosmic web? That question leads us forward. Chapter 19. Is the wall a thing or a pattern? Once the shock of scale is absorbed and the assumptions are questioned, a subtler issue emerges. What exactly is the Hercules Corona Borealis Great Wall? Is it a physical object in the same sense as a galaxy or cluster? Or is it a statistical description imposed on a continuous cosmic distribution? This distinction matters more than it might seem, because it determines whether the structure represents a true violation of cosmological expectations or a boundary artifact of how humans define structure. In everyday language, calling something a wall implies solidity, coherence, and physical unity. But on cosmic scales, structures are not bricks and mortar. They are gradients of probability. The Great Wall is not a contiguous slab of matter. It is a region where galaxy density is higher than average over an enormous volume. The boundaries are not sharp. There is no clear edge where the structure suddenly stops and empty space begins. This immediately complicates interpretation. Any large-scale structure depends on how density thresholds are defined. If astronomers choose a lower threshold, structures appear larger and more connected. If they choose a higher threshold, the same region fragments into smaller components. The Great Wall's reported size depends on where that cutoff is drawn. This does not mean the structure is arbitrary or imaginary. It means its classification reflects human-imposed criteria layered onto a continuous distribution. The cosmic web itself has no labels. It does not distinguish filaments from walls or clusters from superclusters. Those categories exist to help humans describe patterns in a field that varies smoothly across space. The key question then is whether the Great Wall represents a physically meaningful entity or a chance alignment of filaments that appear connected under certain definitions. If the galaxies within it share a common formation history or dynamical relationship, the wall has physical significance. If not, it may be an emergent pattern rather than a coherent structure. Current evidence sits between these extremes. The galaxies forming the Great Wall are connected through filaments of the cosmic web. These filaments trace underlying dark matter distributions, suggesting a real gravitational scaffold. However, there is no indication that the entire structure is gravitationally bound as a single unit. Gravity operates locally, not across a billion light-years. This distinction is crucial. A gravitationally bound structure has a physical identity. It evolves as a unit. The Great Wall does not meet this criterion. Instead, it is a collection of structures that formed independently, but within a correlated region of space, shaped by initial conditions. In this sense, the Great Wall is less like a continent and more like a weather system. It is a large-scale pattern emerging from underlying dynamics, not a single object with a unified fate. This reframing reduces, but does not eliminate, the tension with cosmological principles. If the wall is not a single structure but a connected overdensity shaped by initial fluctuations, its existence becomes more plausible. Rare initial conditions could produce regions where filaments align across vast distances without violating homogeneity globally. The universe remains statistically uniform, but locally extreme. This interpretation aligns with how cosmologists treat voids. Voids can span hundreds of millions of light-years, yet no one argues they are objects in the traditional sense. They are regions where matter failed to accumulate. Walls may be their complementary counterparts, shaped by matter flowing out of voids into sheets. However, the Great Wall pushes this logic to its limits. Its scale suggests correlations extending far beyond what standard models predict. Even if it is a pattern rather than an object, the pattern's coherence remains surprising. Another complication arises from observational selection. The Great Wall was identified through gamma-ray bursts, which trace star-forming galaxies. This biases detection toward regions with high star formation activity. It is possible that other equally large structures exist, but remain invisible because their galaxies are older, quieter, or dust-obscured. In other words, what we see may not be representative of what exists. The Great Wall could be the visible crest of a much broader statistical landscape shaped by observation methods. This possibility weakens claims of uniqueness, but strengthens the argument that large-scale structure is more complex than assumed. Projection effects also matter. Even with redshift information, converting three-dimensional space into two-dimensional maps introduces distortions. Fingers of God effects, redshift space distortions, and peculiar velocities can elongate structures artificially along the line of sight. While careful analyses attempt to correct for these effects, residual distortions remain unavoidable. A structure that appears continuous in redshift space may fragment when viewed in true co-moving coordinates. This does not invalidate detection, but it complicates interpretation. Still, multiple independent analyses using different tracers have identified enhanced density in the same region. This convergence reduces the likelihood that the Great Wall is a pure artifact. It exists as a statistically significant feature, regardless of how it is labeled. What changes then is not whether the structure exists, but how it is understood. The Great Wall may not be a forbidden object violating cosmic law. It may be a natural, though rare outcome of structure formation under extreme initial conditions. This reframing does not absolve theory. Even as a pattern, the wall's coherence must be explained. Why do filaments align across such distances? Why does matter trace such extended correlations? These questions remain unanswered. Importantly, the distinction between object and pattern reflects a deeper philosophical divide in cosmology. The universe is not made of discrete structures stacked hierarchically like building blocks. It is a continuous field shaped by gravity, expansion, and initial conditions. Structures emerge from this field, but their boundaries are human abstractions. The Great Wall exposes the tension between discrete classification and continuous reality. It sits at the boundary where human categories lose precision. Calling it a wall may be less important than understanding the statistical processes that created it. This realization shifts the conversation. Instead of asking whether the Great Wall breaks physics, the more productive question becomes what it reveals about correlations in the early universe. It becomes a probe, not a paradox. In this light, the Great Wall is neither an embarrassment nor a triumph. It is a diagnostic tool. It tests the tails of probability distributions, the limits of Gaussianity, and the scale dependence of homogeneity. Cosmology advances by confronting such edge cases. Average behavior confirms models. Extremes challenge them. The Great Wall lives at the extreme end of cosmic structure, where rare events carry disproportionate information. Chapter 19 therefore reframes the anomaly. The wall may not be a singular object defying the universe's rules. It may be the universe revealing how those rules operate under exceptional conditions. The next step is inevitable. If the Great Wall is a probe of early universe correlations, what does it tell us about inflation itself? That question pulls us further back in time, toward the moment when structure was seeded, and into the next chapter. Chapter 20: Inflation and the Seeds of the Impossible. If the Hercules Corona Borealis Great Wall is not a conventional object, but an extreme pattern imprinted into the cosmic web, then its origins must be traced back to the earliest moments of the universe. Long before galaxies existed, before atoms formed, before light could travel freely through space, the universe underwent a brief and violent episode that shaped everything that followed. That episode is known as cosmic inflation, and it may hold the key to understanding how structures of seemingly impossible size came to exist. Inflation refers to a period of extraordinarily rapid expansion that occurred fractions of a second after the Big Bang. During this phase, space itself expanded exponentially, growing by an enormous factor in an almost unimaginably short time. Regions that were once subatomic in scale were stretched to cosmic proportions. Inflation was introduced to explain several otherwise puzzling features of the universe, including its large-scale uniformity, its flat geometry, and the absence of relics that should have formed in the early universe, but did not. Crucially, inflation also explains the origin of structure. Before inflation, the universe was governed by quantum mechanics. Even in a vacuum, quantum fields fluctuate. These fluctuations are random, unavoidable variations in energy density that occur at microscopic scales. Inflation magnified these tiny fluctuations, stretching them across vast distances and freezing them into the fabric of space-time as density variations. When inflation ended, the universe resumed a slower expansion, but the imprinted density variations remained. Regions that were slightly denser than average began to attract more matter under gravity. Over billions of years, these initial irregularities grew into the cosmic web of filaments, walls, clusters, and voids that define the universe today. Most inflationary models predict that these fluctuations follow a nearly Gaussian distribution. This means that small deviations from average density are common, while large deviations are exponentially rare. The universe should therefore be mostly smooth, with occasional moderate structures and very few extreme ones. The Great Wall appears to challenge this expectation by existing far out in the tail of the distribution. However, inflation does not forbid rare extremes, it merely suppresses them. In a universe as large as ours, even extremely improbable fluctuations can occur somewhere. The observable universe contains an enormous number of independent regions, each seeded by its own set of quantum fluctuations. If the probability of a large fluctuation is low, but non-zero, then the sheer size of the universe makes the existence of at least one extreme structure plausible. This statistical reasoning reframes the Great Wall as a survivor of cosmic chance. It may represent a region where inflation produced an unusually strong density fluctuation, giving structure formation a head start. Gravity then amplified this initial advantage over billions of years, producing a connected pattern that exceeds average expectations without violating physical laws. Yet this explanation raises further questions. Standard inflation models predict a specific spectrum of fluctuations. The amplitude, scale dependence, and correlations of these fluctuations have been measured with remarkable precision through observations of the cosmic microwave background. These measurements show a universe that is almost perfectly uniform, with only tiny variations. If the Great Wall originated from inflationary fluctuations, then either it represents a very rare statistical outlier, or inflation behaved slightly differently than assumed. Some models of inflation allow for non-Gaussian fluctuations, where extreme deviations are more common. Others permit scale-dependent features that enhance structure formation on certain length scales. There is also the possibility that inflation was not a single simple process. Instead, it may have involved multiple fields or phases, producing a more complex pattern of fluctuations. In such scenarios, rare regions of enhanced density could naturally arise without disrupting the overall uniformity of the universe. Testing these ideas requires connecting large-scale structure observations to early universe physics. This is difficult because structure formation involves many intervening processes, including dark matter dynamics, baryonic physics, and cosmic expansion. Nonetheless, extreme structures like the Great Wall act as sensitive probes of inflation's statistical properties. If inflation allowed for larger than expected fluctuations, then similar structures should exist elsewhere, even if they remain undiscovered. Alternatively, if the Great Wall is truly unique, it places tight constraints on how rare such fluctuations must be. Either outcome refines our understanding of inflation. The Great Wall also highlights a subtlety in interpreting homogeneity. The cosmological principle states that the universe is homogeneous on sufficiently large scales, but it does not specify how large sufficiently large must be. That scale is inferred empirically, not defined a priori. Structures like the Great Wall force reconsideration of where homogeneity truly emerges. Homogeneity is a statistical property, not an absolute one. A universe can be homogeneous in expectation while still containing rare anomalies. The presence of a single extreme structure does not negate homogeneity any more than a single heat wave negates the concept of climate averages. What matters is whether such anomalies are consistent with statistical predictions. Inflation provides a framework for calculating those probabilities, but uncertainties remain at the extreme tails of the distribution. The Great Wall occupies precisely that uncertain regime. This uncertainty is not a failure of cosmology, it is a frontier. Inflationary theory has been spectacularly successful, but it is not complete. It does not uniquely specify its own mechanism. Many models remain viable, and distinguishing among them requires precisely the kind of extreme data points that structures like the Great Wall provide. In this sense, the Great Wall is not merely a curiosity. It is a fossil from the earliest moments of time. Its existence encodes information about quantum fluctuations, space-time expansion, and the initial conditions of the universe. By studying it, cosmologists are not just mapping galaxies, they are testing ideas about how reality itself began. The wall bridges the smallest scales of quantum mechanics with the largest scales of cosmic structure, linking the birth of the universe to its present architecture. Chapter 20 therefore places the Great Wall within a deeper narrative. It may not be an error or an exception, but a rare imprint of inflation's randomness. If so, it represents a message from the universe's earliest instant, stretched across 1 billion light-years and 10 billion years of time. The next question follows naturally. If inflation seeded the wall, how does dark matter shape its evolution? That question shifts the focus from initial conditions to the invisible scaffolding that governs cosmic structure, and it leads directly into the next chapter. Chapter 21. Dark Matter as the Cosmic Architect. If inflation provided the initial blueprint for cosmic structure, dark matter is the force that transformed those faint outlines into something tangible. Without dark matter, the universe would look profoundly different. Galaxies would struggle to form, large-scale structure would be far weaker, and vast formations like the Hercules Corona Borealis Great Wall would be impossible to assemble. Understanding the wall, therefore, requires understanding how dark matter behaves on the largest scales. Dark matter dominates the mass budget of the universe. Roughly 85% of all matter does not emit, absorb, or reflect light. Its presence is inferred only through gravity. It shapes the motion of galaxies, bends light through gravitational lensing, and governs how matter clumps over cosmic time. In the early universe, dark matter began collapsing into dense regions long before normal matter could respond. Normal matter initially remained coupled to radiation. Photons exerted pressure on charged particles, preventing gas from collapsing efficiently. Dark matter, unaffected by radiation, was free to respond immediately to gravity. As a result, it formed the first gravitational wells. These wells acted as scaffolding, drawing gas inward once the universe cooled enough for atoms to form. Galaxies grew inside these dark matter halos, tracing their distribution. The cosmic web reflects this process. Filaments and walls are not defined by stars, but by dark matter concentrations. Galaxies illuminate these structures, but do not create them. The Hercules Corona Borealis Great Wall is therefore best understood as a massive dark matter configuration with visible galaxies marking its densest regions. Simulations of structure formation show how dark matter evolves. Starting from inflationary density fluctuations, dark matter collapses hierarchically. Small halos form first, then merge into larger ones. Filaments emerge where matter flows along gravitational gradients. Walls arise where multiple filaments intersect, or where matter accumulates at the boundaries of expanding voids. These simulations reproduce many observed features of the universe with remarkable accuracy. They generate galaxy clusters, superclusters, filaments, and voids in patterns strikingly similar to those mapped by surveys. However, they also reveal limits. Even in simulations spanning billions of light-years, structures exceeding several 100 million light-years are rare. The Great Wall pushes against these limits. To form such an extended structure, dark matter must have remained correlated across enormous distances. This suggests either an unusually large initial fluctuation or subtle effects that enhance coherence during structure growth. One possibility is that dark matter clustering is more efficient than assumed. Most simulations treat dark matter as cold and collisionless. In this framework, particles interact only through gravity and move slowly compared to light speed. Cold dark matter clumps effectively, but its behavior at extreme scales remains uncertain. If dark matter possesses additional properties, its large-scale behavior could change. Self-interacting dark matter, for example, allows particles to scatter off one another. While such interactions are weak, over billions of years they could influence structure formation. Enhanced interactions might promote coherence along filaments, allowing walls to grow larger. Another possibility involves warm dark matter. Warmer particles move faster, smoothing small-scale structure but potentially altering large-scale correlations. While warm dark matter suppresses small halos, its impact on extreme-scale coherence remains an open question. The Great Wall may therefore serve as a constraint on dark matter models. Any viable theory must allow such a structure to exist without disrupting the rest of the cosmic web. This makes extreme structures powerful tests of fundamental physics. Dark matter also influences the wall's longevity. Structures of this scale evolve slowly. The internal motions of galaxies within the wall are governed by the deep gravitational potential of the dark matter scaffold. This helps preserve coherence even as cosmic expansion stretches space. Importantly, the wall is not gravitationally bound as a single object. Expansion dominates at these scales. The galaxies within it are moving apart overall, carried by the expansion of space. What persists is not binding, but correlation. The wall remains identifiable because its density contrast persists relative to surrounding regions. This distinction resolves a common misconception. The Great Wall does not violate gravity's limits by remaining bound across a billion light-years. Instead, it violates expectations about correlation length. The question is not why it holds together, but why it formed as a coherent overdensity in the first place. Dark matter provides part of that answer. Its early collapse, hierarchical merging, and filamentary flow create patterns that can extend far beyond individual clusters. Under the right initial conditions, these patterns can span immense distances. The environment of the early universe may also have favored rapid structure growth. At the epoch when the Great Wall's light was emitted, matter density was higher and cosmic expansion slower relative to structure growth. Gravity was more effective, allowing correlations to develop faster. However, this advantage alone does not fully resolve the scale discrepancy. Even accounting for early conditions, the wall remains extreme. This suggests that dark matter amplified an already rare fluctuation rather than creating the structure from average conditions. The implication is profound. The Great Wall may encode information about both dark matter physics and the statistical nature of the early universe. It is not simply a product of gravity, but a record of how initial conditions evolved under gravity's influence. This dual role makes it scientifically valuable. By studying such structures, cosmologists can test dark matter behavior at scales inaccessible in laboratories. Particle physics experiments probe microscopic properties. Cosmic structures probe emergent behavior over billions of light years. If dark matter behaves exactly as assumed, extreme walls should be exceedingly rare. If they are more common than predicted, assumptions must change. Future surveys will determine which is correct. The Great Wall thus stands at the intersection of observation and theory. It does not overthrow dark matter models, but it pressures them. It forces precision where averages once sufficed. As mapping techniques improve, more such structures may be found. Each discovery will refine our understanding of dark matter's role in shaping the universe. Whether the Great Wall remains unique or becomes part of a broader population will determine how exceptional it truly is. For now, it remains an outlier that demands explanation. Inflation set the stage. Dark matter built the framework. The result is a structure that tests the limits of coherence in an expanding universe. The next step is to examine how cosmic expansion and dark energy interact with such structures. If dark matter builds walls, expansion threatens to erase them. Understanding that balance is essential to interpreting what the Great Wall ultimately means. That balance is the focus of the next chapter. Chapter 22: Expansion, Dark Energy, and the Limits of Coherence. While dark matter constructs the universe's scaffolding, cosmic expansion continuously works to dismantle it. Every structure in the universe exists within this tension. Gravity pulls matter together. Expansion pushes it apart. Understanding the Hercules Corona Borealis Great Wall requires examining how this balance operated when the universe was young and how it continues to shape large-scale structure today. Cosmic expansion is not simply galaxies moving through space. Space itself is stretching. As the universe expands, distances between unbound objects increase over time. On small scales, gravity dominates. Stars remain bound in galaxies, and galaxies remain bound in clusters. On larger scales, expansion overwhelms gravitational attraction, preventing matter from collapsing indefinitely. The rate of expansion has not been constant. In the early universe, expansion was rapid, but matter density was high. Gravity was strong enough to overcome expansion locally, allowing structures to form. As the universe aged, matter diluted, weakening gravity's influence. This shift set an upper limit on the size of coherent structures. Dark energy complicates this picture. It is the dominant component of the universe's energy budget, accounting for roughly 68% of the total. Unlike matter, dark energy does not clump. It fills space uniformly and exerts a repulsive effect, accelerating expansion. This acceleration began several billion years after the Big Bang and continues today. Before dark energy dominated, expansion was slowing under the influence of matter. This era allowed structures to grow efficiently. Filaments thickened. Clusters accumulated mass. Walls emerged at the boundaries of expanding voids. The Hercules Corona Borealis Great Wall formed during this favorable window. The timing is critical. The light we observe from the wall left when the universe was less than 4 billion years old. At that time, dark energy had not yet taken control. Matter still governed cosmic dynamics. Expansion was present, but gravity could still amplify large-scale correlations. Even so, expansion imposed limits. Gravity propagates at finite speed. Matter separated by extreme distances cannot influence each other instantly. The age of the universe sets a horizon beyond which structures cannot become causally connected. This horizon constrains how large coherent features can grow. The cosmological principle emerges from this reasoning. On sufficiently large scales, matter distribution should smooth out. Density fluctuations average away. Structures larger than a few 100 million light-years should dissolve into statistical uniformity. This expectation underpins modern cosmology. The Great Wall challenges this expectation not by remaining gravitationally bound, but by remaining identifiable. Its galaxies are not collapsing into a single object. They are receding from each other under expansion. What persists is an overdensity pattern embedded in the expanding universe. This distinction is subtle but essential. The wall is not resisting expansion. It is expanding with it. The galaxies within it move apart, but they do so in a correlated way. Their relative overdensity remains detectable against the cosmic background. Dark energy intensifies this process over time. As expansion accelerates, matter becomes increasingly isolated. Structures stop growing. Existing walls and filaments freeze in place, stretched by expansion but no longer accumulating mass. In the distant future, even clusters will become isolated islands in an ever-expanding void. From this perspective, the Great Wall represents a fossil. It is a snapshot of structure formation near its upper limit. Its existence implies that the universe briefly allowed correlations to extend farther than expected before dark energy curtailed further growth. This raises an important question. Is the wall a product of ordinary physics operating at extreme statistical limits? Or does it hint at subtle deviations in cosmic expansion history? Some models propose that dark energy was weaker in the past, or evolved over time. If expansion accelerated later than assumed, matter would have had more time to organize. Structures could grow larger before being frozen in place. Observational evidence places constraints on such models. Measurements of supernovae, cosmic microwave background, and baryon acoustic oscillations suggest dark energy behaves like a cosmological constant. However, small deviations remain possible within uncertainties. Even slight differences in expansion history can have large effects on structure growth. A marginally slower expansion rate in the early universe would allow gravity to amplify correlations more efficiently. Over billions of years, these differences compound. The Great Wall may therefore serve as a sensitive probe of expansion dynamics. It encodes information about how quickly the universe transitioned from matter domination to dark energy domination. Its size and coherence reflect how long gravity remained competitive at large scales. Importantly, this does not imply that expansion failed. The wall exists within an expanding universe and obeys its rules. What it challenges is where the boundary between coherence and homogeneity truly lies. Expansion also affects how we observe the wall. The structure is not seen as it exists today, but as it existed 10 billion years ago. During the time light traveled toward us, space continued expanding. The present-day separation between its galaxies is larger than when the light was emitted. This stretching complicates interpretation. The wall we observe is already an expanded version of itself. Its original configuration was more compact. This reinforces the idea that it formed early and has been stretched rather than assembled recently. Expansion, therefore, acts both as a limit and a preservation mechanism. It prevents further growth, but preserves the imprint of early correlations by freezing them into the cosmic fabric. The interaction between dark matter and expansion defines the largest structures we can observe. Dark matter builds patterns, expansion halts them. Dark energy ensures those patterns never fully collapse. In this framework, the Great Wall is not an impossibility, but an extreme outcome. It occupies a narrow window where gravity briefly outran expansion on immense scales. Whether this outcome is rare or inevitable remains uncertain. If initial density fluctuations occasionally exceeded average values, some regions would naturally produce oversized structures. Given the vast volume of the observable universe, rare outcomes become observable. This statistical interpretation preserves the cosmological principle as an approximation rather than an absolute law. Homogeneity holds on average, but fluctuations exist. The Great Wall represents one such fluctuation near the extreme tail of possibility. The alternative would require revising expansion physics itself. That would have sweeping consequences, affecting everything from cosmic age estimates to dark energy models. At present, evidence does not demand such revisions. Instead, the wall sharpens questions. How rare are extreme structures? How sensitive is structure formation to expansion history? Where precisely does homogeneity emerge? Answering these questions requires mapping the universe with greater precision. Upcoming surveys will measure millions of galaxies across vast volumes, refining our understanding of large-scale coherence. As data improves, the Great Wall will either stand alone or be joined by similar discoveries. Its significance depends on that outcome. For now, it remains a boundary case. It exists at the edge of what expansion allows. It records the moment when gravity's reach briefly extended farther than expected. In doing so, it reminds us that cosmic rules describe tendencies, not guarantees. Expansion shapes the universe, but it does not erase all structure. Within its vastness, rare patterns persist. The next chapter turns to the observational methods that revealed the Great Wall in the first place. Understanding how such a distant structure was detected is essential to evaluating its reality and limits. Chapter 23: Observational Bias, Statistics, and the Risk of Cosmic Illusions. When astronomers encounter structures that challenge theoretical expectations, the first response is not revision of physics, but scrutiny of observation. The universe is vast, data is incomplete, and human pattern recognition is powerful. Before the Hercules Corona Borealis Great Wall can be treated as a genuine cosmological challenge, its detection must survive the most demanding statistical and methodological tests. Large-scale structure is not observed directly as a physical object. It is reconstructed from data points, galaxies, quasars, gamma-ray bursts. Each of these is a tracer, not the structure itself. The wall emerges only when thousands of individual detections are combined and interpreted within a statistical framework. This process is vulnerable to bias. The Great Wall was initially identified through the spatial distribution of gamma-ray bursts. These events are extraordinarily luminous and can be observed across vast cosmic distances. Their brightness makes them useful probes of the distant universe, but their rarity introduces complications. Gamma-ray bursts are not evenly distributed. They occur preferentially in galaxies with active star formation and massive stellar populations. This introduces selection effects that must be carefully modeled. If gamma-ray bursts were randomly distributed, clustering would be suspicious. But they are not random. They trace specific astrophysical environments. An apparent overdensity, could reflect astrophysical bias rather than genuine large-scale structure. To address this, astronomers compare observed distributions with simulated catalogues that include known biases. They ask whether the clustering exceeds what would be expected given the number of detections, survey geometry, and underlying astrophysical processes. For the Great Wall, multiple independent analyses concluded that the clustering was statistically significant. Still, significance does not imply certainty. Statistical confidence depends on assumptions. One critical issue is a posteriori selection. The structure was identified after examining the data, not predicted in advance. This increases the risk of overestimating significance. When many possible patterns are searched for, some will appear meaningful by chance. This is known as the look elsewhere effect. If you examine enough regions of the sky, one region will inevitably stand out. Proper statistical analysis must account for how many opportunities existed to find such a structure. Researchers attempted to address this by comparing the observed clustering against randomized catalogues across the full sky. The probability of producing a structure of comparable size and density by chance was found to be low, but not zero. This places the Great Wall in a gray zone between anomaly and outlier. Projection effects present another challenge. The universe is observed in redshift space, not true three-dimensional space. Redshift combines cosmic expansion with local velocities. Galaxies moving toward or away from us, due to gravitational interactions, can appear displaced along the line of sight. This can artificially elongate or compress structures. However, the Great Wall's extent is primarily transverse rather than radial. Its length spans the sky, rather than extending along the line of sight. This reduces the likelihood that redshift distortions alone could produce its apparent size. Incomplete sampling also matters. The wall lies at high redshift, where galaxy surveys are less complete. Missing galaxies can exaggerate perceived contrast. Conversely, sparse sampling can cause disconnected structures to appear continuous when interpolated. To mitigate this, astronomers rely on independent tracers. The wall's signal appears not only in gamma-ray bursts, but also in galaxy overdensity maps derived from optical and infrared surveys. While these datasets are less complete, their consistency strengthens the case for a real structure. Still, uncertainty remains. The boundaries of the wall are not sharply defined. There is no physical edge. Density declines gradually. Deciding where the structure begins and ends requires threshold choices. Different thresholds yield different sizes. This ambiguity complicates comparisons with theoretical limits. If the wall's effective size depends on definition, claims of violation become sensitive to methodological choices. Critics argue that with stricter thresholds, the structure becomes less extreme. Supporters counter that even conservative definitions leave the wall unusually large. The debate reflects a broader issue in cosmology. Structures are continuous, but models rely on discrete classifications. Another concern is confirmation bias. Once a structure is proposed, subsequent analyses may unconsciously favor its existence. This is why independent teams using different methods are essential. For the Great Wall, such independent confirmations exist, but none are definitive alone. The risk of illusion is not hypothetical. History includes examples of structures that later dissolved under improved data. Early galaxy maps suggested immense walls that later fragmented when deeper surveys revealed gaps. Apparent coherence can fade with resolution. Yet the opposite has also occurred. Structures once thought illusory became accepted as data improved. The Sloan Great Wall followed this trajectory. Initial skepticism gave way to acceptance as evidence accumulated. The Hercules Corona Borealis Great Wall sits between these precedents. It is more extreme than previous structures, but supported by multiple lines of evidence. Its distance complicates confirmation, but its scale makes dismissal difficult. The key question is not whether uncertainty exists, but whether uncertainty is sufficient to nullify the challenge. At present, it is not. The wall remains statistically unusual, even after accounting for known biases. This does not mean physics is broken. It means observation has reached a regime where rare events become visible. In large datasets, the tails of distributions matter. The Great Wall may reside in that tail. Cosmology increasingly operates in this regime. Precision measurements have narrowed theoretical expectations. Deviations once hidden in noise now stand out. The universe appears orderly on average, but individuality emerges at extremes. Statistical outliers are not failures of theory. They test robustness. A theory must accommodate not only typical outcomes, but also rare ones. The question is whether the Great Wall exceeds what reasonable extensions of current models allow. At present, the answer remains open. The wall strains models, but does not snap them. Its existence motivates refinement, rather than rejection. The next step is accumulation. If future surveys reveal multiple structures of comparable scale, the balance will tip. One outlier may be chance. Many suggest revision. Upcoming observatories will provide that test. They will map larger volumes with greater completeness. The cosmic web will be traced with unprecedented fidelity. Until then, the Great Wall occupies an uncomfortable position. It is too large to ignore and too uncertain to overthrow foundations. It demands caution without complacency. Cosmology advances not by certainty, but by tension between expectation and observation. The Hercules Corona Borealis Great Wall exemplifies this tension. The next chapter examines what this structure implies for the cosmological principle itself. Whether it survives intact or must be reframed depends on how we interpret such extremes. Chapter 24. The Cosmological Principle Under Pressure. At the foundation of modern cosmology lies an assumption so basic that it is often treated as background rather than theory. This assumption is known as the cosmological principle. It states that when viewed on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means that no location in the universe is fundamentally special. Isotropic means that no direction is preferred. Together, these ideas assert that the universe looks statistically the same everywhere when averaged over large enough volumes. This principle does not deny the existence of structure. Galaxies, clusters, filaments, and voids are all expected features. What it constrains is their scale. Beyond a certain size, these structures should blend into uniformity. Local irregularities should cancel out, leaving a smooth cosmic average. This expectation is not philosophical. It emerges from both observation and theory. The cosmic microwave background provides the strongest evidence. Its temperature variations are extraordinarily small, on the order of 1 part in 100,000. This uniformity suggests that the early universe was remarkably smooth. From these initial conditions, structure grew gradually under gravity. Simulations based on these conditions consistently show that coherence fades beyond a few 100 million light-years. This is where the Hercules Corona Borealis Great Wall becomes problematic. Its scale appears to exceed the length at which homogeneity should dominate. If it is truly coherent over more than 1 billion light-years, then the scale of cosmic uniformity is larger than expected. This does not automatically falsify the cosmological principle, but it weakens its empirical grounding. The principle was never meant to be exact. It is an approximation. The question is, how approximate it can be before losing explanatory power. If the universe contains rare but enormous deviations from homogeneity, then the principle may still hold statistically, but its predictive clarity diminishes. One way to reconcile the Great Wall with the cosmological principle is to treat it as a statistical fluctuation. In this view, homogeneity emerges only when averaged over extremely large volumes, and rare deviations can exist below that threshold. The universe remains homogeneous in the mean, even if local extremes occasionally occur. This interpretation depends on probability. If structures of this scale are sufficiently rare, then their existence does not violate the principle. The challenge is determining rarity. With only one or two known examples, statistical certainty is limited. The observable universe is large enough that even low-probability events may occur once. However, the cosmological principle is not just a statistical claim. It underpins the equations that describe cosmic expansion. The Friedmann-Lemaitre-Robertson-Walker metric assumes large-scale homogeneity and isotropy. This framework successfully explains cosmic expansion, nucleosynthesis, and background radiation. Abandoning it would require reconstructing the mathematical foundation of cosmology. This makes theorists cautious. Rather than discarding the principle, they explore ways to refine it. One approach is scale dependence. The universe may only become homogeneous at larger scales than previously estimated. Early estimates placed this scale around 300 to 400 million light-years. The Great Wall suggests it could be closer to 1 billion. Another approach is anisotropic inflation. If inflation generated slightly larger fluctuations on certain scales, then large structures could form without breaking overall isotropy. This would preserve the principle in a generalized form while allowing rare extremes. There is also the possibility that what appears as a single structure is not dynamically unified. The Great Wall may consist of multiple independent filaments aligned by chance. If so, coherence is observational rather than physical. The universe remains homogeneous in its dynamics, even if patterns appear visually continuous. Testing this requires detailed mapping of internal velocities and histories. If galaxies across the wall share correlated motions or formation timelines, physical coherence is more likely. If not, the appearance of unity may dissolve under scrutiny. The cosmological principle also interacts with dark matter assumptions. Structure formation is governed largely by dark matter distribution. If dark matter behaves differently on large scales than current models assume, then structure limits may shift. This would alter expectations without requiring abandonment of homogeneity. Importantly, the principle has survived challenges before. The discovery of superclusters, voids, and walls initially shocked astronomers. Each time, the principle was refined rather than rejected. The universe revealed more structure than expected, but still averaged toward uniformity at larger scales. The Great Wall represents the latest and most severe test. It pushes the boundary further than previous discoveries. Whether it crosses that boundary depends on future evidence. If upcoming surveys reveal that homogeneity only emerges beyond scales larger than previously thought, the principle will adapt. If many such walls are found, the principle will weaken. If none are found, the Great Wall may remain a singular anomaly. What matters is not comfort, but consistency. A principle must accommodate data, not the reverse. The cosmological principle has endured because it has repeatedly absorbed new observations without collapse. At present, it remains intact but strained. Its domain of validity is under examination. The Great Wall does not overthrow it, but it forces precision where assumption once sufficed. This pressure is productive. It sharpens theory and motivates deeper surveys. It encourages humility in claims of cosmic simplicity. The universe may be homogeneous only in a statistical sense, with rare but dramatic exceptions. Or it may be less uniform than assumed, with structure extending farther than models predict. Both possibilities preserve much of cosmology while demanding refinement. The cosmological principle was never a claim of perfection. It was a working assumption grounded in evidence. That evidence is now being tested at unprecedented scales. The Hercules Corona Borealis Great Wall stands as a reminder that foundational ideas must remain responsive to observation. Principles survive not by resisting anomalies, but by accommodating them honestly. In the final chapter, the focus shifts from theory to perspective. What this structure ultimately represents may be less about breaking physics and more about revealing the limits of what we assumed the universe would allow. Chapter 25. what the wall ultimately tells us. The Hercules Corona Borealis. Great Wall does not announce a collapse of cosmology. It does not invalidate gravity, overturn general relativity, or dismantle the standard model of the universe. What it does instead is far subtler and, in many ways, more important. It exposes the boundary between what modern cosmology explains comfortably and what it explains provisionally. It reminds us that even our most trusted frameworks operate within limits that are still being mapped. At its core, the Great Wall forces a reassessment of scale. Not the scale of individual objects or even of galaxy clusters, but the scale at which cosmic order transitions into statistical uniformity. For decades, that transition was thought to occur well below 1 billion light-years. Observations supported this view. Simulations reproduced it. Theory reinforced it. The Great Wall does not erase those foundations, but it extends the question further outward than anticipated. This distinction matters. Cosmology does not rest on absolute uniformity, but on predictable averages. The universe can tolerate irregularities as long as they remain statistically rare. The unresolved issue is whether the Great Wall represents a rare tale of expected variation or a signal that the distribution itself allows more extreme outcomes than models predict. That difference separates refinement from revision. Importantly, the wall's existence does not appear to be the result of observational error. Multiple independent analyses using different tracers and methods converge on the same conclusion. There is a significant overdensity of matter across a vast region of space at a specific epoch in cosmic history. While the exact boundaries and internal structure remain under study, the phenomenon itself is difficult to dismiss as noise. Nor does the Great Wall appear to be a simple artifact of projection. Its coherence persists across redshift slices, indicating that it is not merely a line-of-sight illusion. The structure has depth, internal organization, and continuity. These features imply a real feature in the large-scale distribution of matter. At the same time, caution remains essential. Cosmology has a history of over-interpreting early discoveries. Structures once thought singular later proved to be part of broader patterns. What appears exceptional at one moment may appear typical once larger datasets become available. The Great Wall exists near the current observational horizon, where selection effects, sampling limits, and statistical uncertainties are strongest. Future surveys will determine whether this structure is alone or part of a population. If similar scale walls are found at comparable epochs, the argument for revision strengthens. If not, the Great Wall may remain an extreme but permissible anomaly. This uncertainty reflects the true nature of scientific progress. Science advances not by declaring certainty prematurely, but by holding competing explanations in tension until evidence resolves them. The Great Wall occupies precisely that space. It is neither dismissed nor fully explained. It is a boundary object, marking where understanding thins. There is also a temporal dimension to its significance. The wall is observed as it existed when the universe was less than a third of its current age. Structure formation was still underway, galaxies were younger, interactions more frequent, and matter more densely packed. Conditions were more favorable for rapid growth, yet still constrained by expansion and causality. That such a large structure existed so early adds weight to the challenge it poses. This timing suggests that whatever processes contributed to the wall's formation acted efficiently and early. Whether this reflects rare initial density fluctuations, subtle features of inflation, or unmodeled behavior of dark matter remains unresolved. Each possibility carries different implications, and none currently contradict known physics outright. The Great Wall also highlights the role of dark matter as the universe's structural scaffold. Galaxies trace dark matter, not the other way around. If visible matter forms a wall, then dark matter formed one first. Understanding how dark matter arranged itself on such scales provides constraints on its properties. This is not merely an academic concern. It connects the largest structures in the universe to the smallest unresolved questions in particle physics. There is a philosophical lesson embedded here as well. Cosmology often speaks in absolutes, The universe is homogeneous, isotropic, flat. These statements are true in context, but incomplete without qualifiers. The universe is homogeneous beyond a scale that must be measured, not assumed. Isotropy emerges statistically, not locally. Flatness holds within observational precision. Each claim is conditional. The Great Wall reminds us that cosmic simplicity is an emergent property, not a given. Order arises from complexity, not the absence of it. The universe organizes itself through competing forces acting across enormous scales over immense spans of time. Occasionally, that process produces outcomes that sit at the edge of expectation. Such outcomes are not failures of theory. They are tests of its scope. From a human perspective, the wall also reframes scale in a visceral way. A structure more than 1 billion light-years long is not merely large. It dwarfs all familiar cosmic landmarks. Entire superclusters fit inside it. Millions of galaxies inhabit it. The distance light has traveled to reach us from it exceeds the time complex life has existed on Earth. It is a reminder that human intuition evolved for environments radically different from the cosmos we now study. Yet despite this mismatch, we are capable of understanding it. We can detect patterns across billions of light years. We can reconstruct cosmic history from faint signals. We can confront anomalies without abandoning coherence. That capacity is one of science's quiet triumphs. The Great Wall does not make the universe chaotic, it makes it richer. It shows that even after a century of cosmological progress, the universe retains the ability to surprise us at fundamental levels. That surprise is not a threat to understanding, it is its engine. As observational reach expands, more boundaries will be tested, new structures will be found. Some will conform, others will challenge. The task of cosmology is not to enforce simplicity, but to describe reality as it is, even when that reality resists tidy limits. In that sense, the Hercules Corona Borealis Great Wall is not an embarrassment to cosmology. It is a milestone. It marks how far understanding has come and how much further it must go. It stands as evidence that the universe is not obligated to conform to our expectations, only to its own laws. And those laws, whatever their ultimate form, are still being uncovered. The wall exists. It stretches across deep time and vast space. It does not break physics, but it presses against its edges. In doing so, it fulfills one of science's most important functions, reminding us that knowledge is provisional, that certainty must remain flexible, and that the universe is always larger than the models we build to describe it.